Last class, I had you guys do that simulation for applied forces and static friction and kinetic friction. So you looked at that, you got a chance to see and get an idea of it. Now let's actually get into the nitty-gritty here. So we're going to look at 4.6 and 4.7 together. 4.6 and 4.7 really get into free body diagrams, motion, forces, but then in 4.8 we're going to look at friction. So for the next section for today and probably part of Thursday's class, we're going to look at this section, but it's really nothing to do with friction yet. So I don't want you to jump the gun on the lab. Hold on to the lab still in case you want to go back and edit anything to do with friction, but we're not going to get to that until 4.8. So that won't be due for a little while. So the main things we're going to look at, free body diagrams, we're going to look at equilibrium problems, we're going to talk about weight versus mass and how they differ. We'll talk about what's called the normal force, and then tension. Tension is the last thing we're going to end on with this lesson. So let's start right away. So first, a free body diagram. A free body diagram is a diagram showing forces acting on an object. Acting on an object. So, the diagram on the left is not a free body diagram. The diagram on the left is called a force diagram. A force diagram shows all forces acting for an entire problem. So there might be a problem where, how many people have played billiards or pool before, right? Okay. So you're playing pool and you have a combo shot. So you're hitting the cue ball, and say you have to hit the cue ball into a solid, which is what you are shooting for, which then hits a strike, which then hits a solid, right? You don't want to scratch hit the wrong ball first. So you have a combo shot. And during that combo shot, there are a lot of interactions. The cue ball hits the first ball hits the second ball, which is like the transfer one, and then the second one hits the third one, which is what your target ball actually is. During that process, there are forces acting on all of those billiards balls. All four of them have forces acting on them. The first one is what you strike it with to start. It starts to move, it hits the first billiards ball. It gets rebounded slightly. The first billiards ball hits the next one, which hits the next one. It involves like a chain reaction. So when we look at these diagrams, if I looked at all of the billiards balls at once, I would be looking at what's called a force diagram. But if I specifically said, let's focus on the cue ball, for example, and we only look at the cue ball. So the cue ball would only have an applied force to start, some slight friction, very little because it's rolling. Then when it hits the first ball it's supposed to hit, it would have an applied force backwards or against its motion. So when we look at a free body diagram, we're looking at the diagram shown here on the right. This is the free body diagram of the car itself. So on the left, we see the car and we see the wall. We see both of those things. But on the right, we see only the car. Yeah.
You said that, you mentioned it briefly, just that if something is rolling, it doesn't have as much friction. So why does a car have so much friction?
Well, that's different. So a car that rolls on tires, if you don't hit the brakes and you just let the car coast, it'll coast for a while. Eventually, stop it. It will come to rest because there's internal friction in the axle, in the engine, with the pistons. There's a lot of frictional losses. But when something rolls traditionally, it exhibits much less sliding friction. So when I take an object and slide it across like that, that exhibits what's called kinetic or sliding friction. But if it were one of those carts that we've looked at and I did the same thing, it would not stop as easily because it's rolling. So when an object is rolling, its kinetic friction or its sliding friction is very, very, very low. Almost zero. It's really the friction that's lost in the axle and the turning of the wheel. Now, rolling friction is a whole other topic, and we'll get to rolling friction. And that provides some propulsion forward. Like when you walk, right? When you physically walk, you're pushing. You're literally pushing every time, whether you realize it or not. A car tire is doing the same thing. When a car tire starts to roll, the rubber in the tire grips the ground, and it pushes off the ground each time. So as a car tire rolls very slowly, if you want to think about it, every time it's in contact with the ground, there's friction pushing back against the ground, which is propelling the car forward. Okay, so there's a lot more friction in sliding and rolling than you think. Okay? Now, for this example here, this car on the right is the object of interest. So the way we're going to draw things in this class is with a dot showing the center of mass of the object, and then we're going to draw all of our forces acting from that dot. So the force acting to the left is a force on the object. Well, I might call it F in this case. I'm going to call it FW for wall. the force from the wall acting against the car when it hits the wall. Then here we have the force due to its weight, which is called gravity. And we're going to get into that in a moment. We're going to get into all these types of forces, I promise. And then what we have is the floor pushing back up. The floor pushing back up. And we're going to call that normal force, and we'll talk about that in a moment as well. But just to give you an idea of what this diagram is really indicating, when you're sitting in your chair, why aren't you just falling down to the ground? Because your chair is supplying a reaction to your body's desire to want to fall. You're in a gravitational field right now. So if I were to literally just pick up this case and drop it, it falls. But if I had my hand beneath it and I drop it, it doesn't move. Because my hand is supplying some sort of a reaction to keep it there. I have to apply an upward force, and that upward force comes from the tension in the muscles in your arm. So the tension in the muscles in your arm translates to your hand. The muscles, ligaments, and tendons, all that stuff in your hand are what are keeping this in place. Well, when a chair pushes back against you, we simplify it. We call it a normal force. A normal force, meaning a reaction. And we'll get into normal force a little bit, but those are the three forces that are acting on this car. The wall, which is stopping its horizontal motion. Gravity, which is pulling it down. And the floor, which is pushing back up. Now, technically speaking, if we look at the floor here, that should not be locked, sorry. When we look at the floor here, the floor is actually in contact with the car in 4 different locations. Each tire. Every tire is a different placement or a different amount of force being distributed. So each tire is technically carrying a quarter of the weight of the car. Think about your feet, right? Why is it so much tougher to stand on one foot?
All of your weight is on one foot.
Versus
Balance between two.
Yeah. With 2 feet, you can balance. You can balance left to right. You can balance kind of forward and back, not as much. You notice that on the subway? Everybody notice that on the subway, right?
Yeah.
If your only direction is balanced one way, you're going to fall. So you need to either be leaning against the door, which everybody loves that spot on the subway, right? Because you can't move left to right because your feet are there. You're pushing back with friction. The door's pushing you back. You're stable. Or you need to be, if the train is moving this way, your feet need to be this way, and you have to be holding a pole like this. The pole prevents you from moving left to right. The feet prevent you from moving front to back. So when we talk about stability here, this car specifically has 4 stability points. The tires each take on a quarter of the weight of the object. This is the object's weight right here. Okay, so let's get into the definitions and other stuff. We're going to actually do this. So start with the phrase equilibrium, which we've talked about already. Equilibrium is a balance. In chemistry, you talked about temperature equilibrium. And simply put, when the temperature of 2 substances that are separate are the same temperature. They reach what's called temperature equilibrium, or thermal, to be more specific, thermal equilibrium. And when does this happen? You drop an ice cube into a cup of water, eventually what happens to that ice cube? It melts. And the cup of water eventually is 1 overall temperature. Whereas initially, the ice was a very cold temperature, or low temperature. So it was absorbing the heat, and then the hotter substance that it was in was actually giving its heat to the ice. That's a whole other idea of exothermic and endothermic processes. But the idea behind it is that they eventually reach thermal equilibrium, which is when the temperature of the fluid, or liquid in this case, and the temperature of the ice cube eventually match up. In this course, we're going to specifically, in mechanics I should say, in mechanics, because we'll get into thermal stuff maybe later in the year. In mechanics, we're going to talk about force equilibrium. Force equilibrium is seen all the time. You're seeing it right now. You're exhibiting it right now. Again, your weight wants you to fall to the ground, but why aren't you again? What's holding you there? Physically, what's holding you there? Not the force, but physically, what is it? The chair. So the chair pushing up balances your weight pushing down. So we would say you're in a state of vertical equilibrium. Vertical, right? We need to know the definition of vertical and horizontal, as we keep saying. You're in a state of vertical equilibrium. Now, horizontally, you're also in a state of equilibrium, but unless you physically push yourself left to right, there's no forces at all acting on you horizontally right now. But there's always always a vertical force acting on you, I should say, if you're on a planet, or if you're within the gravitational pull of a planet. If you're just out in outer space, there is nothing pulling you toward the ground or toward the surface, except the closest planet nearby, and that gets into like how close are you to the planet, if gravity affects you or not. But on Earth, on a planet, the idea is that you are always feeling your weight pulling down on you. There's always a vertical force acting on a body, and that is that force called weight. Well, normal force pushes back, that's what equilibrium is. What's an example of equilibrium outside of what we just gave here? What's an easy example you can think of equilibrium? Yeah?
Economics, I guess, like on a graph.
What you're talking about, like what?
Like the money you invest, the profit you make, and then the equilibrium to see where it is.
Yeah, that's a great idea. That's a great example. When you think about what's called the break-even point, okay? When you think about when your revenue eventually exceeds your cost, you have a portion, it's called a profit margin for that reason. There's a margin of a gap each time, and eventually they equate. That would be considered equilibrium. Good example, yeah.
Parked car.
Say again?
A parked car.
A parked car is in equilibrium in several ways. What if it's parked at an angle, Maura? And how do you keep it in equilibrium?
The brakes are pushing back in the other direction.
Yeah, you put on the emergency brake usually when you're parked at an angle, because there is a chance the car could start to slide, and the e-brake is a stronger brake applied to your car wheels. What else?
When you finish a bungee jumping, you just dangling at the bottom.
Yeah, that's a great example. During the bungee jump, a lot of forces are acting on you, right? But eventually what happens? You eventually just settle out, you're hanging there, right? So your weight pulling down is balanced by the spring force pulling up. A bungee is a spring. Think about a spring, right? Like a slinky, a spring. A bungee is just a spring. So we're going to talk about Hooke's law, which is spring forces later. So yes, the spring force pulling up would be balancing the weight pulling down. There are infinitely many examples. I'm just trying to get you guys thinking outside the box as to where you could see equilibrium. The simplest one that a lot of students like to think of is a tug of war. When a tug of war is in a stalemate, think about what is that called? Color wars, right? You know what I mean? When you have a tug of war, if you're physically not moving, it means that the force applied in both directions is the same. They're balanced. Okay? They're balanced with each other. Let's keep going. We talked already about action-reaction pairs, but let me again just reiterate. This is Newton's third. Newton's third law told us about the concept that for every action there's an equal and opposite reaction. So I gave the example of a person jumping on the earth. Right? Do you remember the example I gave? I said how you kind of move the earth because there's a force acting up on the earth. Let me give another example for this. So the other example I like to go through is thinking about a hammer with a nail. So let's start by drawing, for now, I'm just going to draw, God bless you. I'm going to draw a surface. Those lines mean that to the right of this is a solid surface. You'll see this a lot in physics. Okay, those slash lines like that. I could also draw it like this, which means that that's a ceiling up top. Okay, that just means it's a surface that you can't get through. So let's say I'm going to blow up this image a lot. I'm going to blow it up. So let's say this is our nail here. That'd be a huge nail. I mean, I guess relative to the surface, we don't know, but the hammer would be enormous then, right? So the hammerhead would be bigger than the nail. So if I were to draw the hammer that's actually hitting this nail, the hammerhead would be like, and it's got that claw on the end of it, and that would be like the hammer like that. Not bad, actually, my art skills. It looks like a mallet more than a hammer. So you're hitting on this nail, right, with a hammer. So if I were to think about this, and I were to use Newton's third law, I'd say, well, for every action, there's an equal and opposite reaction. So when I hit the nail with the hammer, the nail hits me back with the same force on the hammer itself. So we know that when this hammer strikes the nail, if I were to draw the hammer here, on the right I'm going to draw free body diagrams, and the nail over here. Let's take a look at our free body diagram for both of these. So first, the nail physically feels a force from the hammer that's acting on the nail itself. It's physically acting on the nail. That force is directing it into the wall. So this is a force. I'm going to say just FH for now, the force of the hammer. I don't want to get into too much nitty-gritty substance, just the force of the hammer. Okay. Now, that same force applied by the hammer on the nail comes back against the hammer itself. and that's the force from the nail. So those are my pairs right there. That's my pair right there. That's my pair of balanced forces, my action-reaction. Again, the hammer applies a force to the nail to the right. The nail responds by applying a force on the hammer to the left. But here's the thing. If I were to then draw the rest of the forces acting, I could see, why does this nail accelerate? Because the wall pushes back against the nail, but with very little force. The wall can't withstand the force of the hammer acting on the nail. So therefore, the nail penetrates the surface of the wall and embeds itself. So this is because FH is greater than FW. The hammer hitting the nail is stronger than the wall hitting back on the nail. Sure, the nail still hits the hammer back with the same force it applied. FH is equal in magnitude to Fn. They're the same thing. If FH is 10 newtons, Fn, feeling the pushback, is 10 newtons. If you've ever fired either a regular gun or a BB gun, or even something like a water gun, like a super soaker or a Nerf gun, there's recoil for all things. Anybody know the term recoil? Does that ring a bell? Recoil? How would you describe? Show me physically what recoil would look like. What would it look like? Show me. Right? This is what you see when you think of recoil. Recoil is the concept that the gun is propelling the bullet forward. So the bullet wants to propel, the gun is propelling the bullet forward, so the bullet wants to propel the gun backward. That's the action-reaction pair. So you feel this recoil, this force backward on you, just like the hammer. If you've hammered before, you know this, and this is like an unfortunate thing. People have accidentally hurt themselves at times. If you hammer, and you hammer hard enough, the hammer's going to rebound off the nail sometimes. Because again, the nail is pushing back on the hammer. And if you hammer hard enough, it can rebound and hit yourself physically, like in the face. So that's why when you hammer, you never hammer with your face, like you never hammer like this. Because if it rebounds, you're going to smack yourself in the face with it. So when you hammer on the side, and then your location on the hammer changes based on torque, which we'll talk about a little bit later in the year.
The play last year, I took the recoil too early and the sound effect didn't come in. And I was like, oh.
And you were like this, and then the sound effect?
Yeah, I was like, darn it.
But the recoil, you have to act it out because you know what would happen in physics.
Then they told me to not do the recoil because then the cue would be wrong.
Timing for it?
Okay.
So in this case, the hammer, why isn't the hammer going to actually propel you and hit you back in the face? Because you are holding it. You are an applied force. So if your applied force in green here can balance, I'm going to say FP for a push. If the push you give it after it hits the nail can balance the recoil that it has, it's not going to recoil against you. So again, Fn and FH are the action-reaction pairs here. That's the action-reaction pair. Everything else going on in this arrangement has to do with external things. The wall, that's an external thing. That's a force applied against you. You holding it, you hitting, and physically after the hammer strikes the nail, you preventing it from doing this, like by physically holding it, that's FP. FW and FP are these external forces outside of the action-reaction pair. But FH and Fn are equal and opposite to each other. Guaranteed, they have to be. Their values are the same, but they're in opposite directions. That's the whole concept of Newton's third law.
Is there a vertical arrow on this?
On this diagram, we could technically say that, but that's not of interest right now. But yes, theoretically, the weight of the hammer acts down, so you would have to apply a force upward also. So there would be Fg pulling down, and Fp2 instead of Fp1, another applied force, you vertically holding it upward. Same thing with the nail technically, you have to hold it there with your fingers, right, beforehand? So gravity pulls down, but this, you holding it there is technically applying force upward to balance it. I'm not drawing it though just because we're not interested. Yep. Or just because it's not that it's small, it's just that Jack right now, that's not the focus of the problem. So I'm not drawing them here. Because I'm not, yeah, exactly. To discuss what I want to discuss, I didn't need the y direction, so I'm not drawing for that reason. But for any other free body diagram this year, we draw all forces acting on it for any given scenario. This is just a different, this is like an example where you might see it as well.
So on the Earth, is there ever an example where there's like no external forces?
Where there's no external forces?
Yeah, because isn't there always going to be some minute external force?
It's a great question, George. What do you think? where there would be no external forces. I mean, gravity acts on all objects, so technically speaking, there's always gravity. So no, there would never be a situation where there's no external. Could the external forces balance each other? Sure. Gravity balanced by the spring force of the bungee. That's a balanced equilibrium. But technically, those are both external forces. If the net overall external force is zero, though, that's where equilibrium comes into play. But yes, technically speaking, everything has an external force acting on it. Everything. Even objects that are at rest. Valentina.
Do force of the hammer and force of the wall have an action-reaction pair, or you said
No. So, again, the force of, you're talking about these two right here?
Yeah.
Yeah, those do not have a third force as a pair. So, the wall, okay, let's think about this for a second. The wall is providing this response because it's a rigid member. It's not, let me think for a second. The wall itself is not an action. The wall itself pushing back would not be considered an action. So, it's a great question, right? Remember the paragraph for that one. Because Newton's third law says all
Yeah, that's
in pairs, yeah. I guess technically if we drew a free body diagram of the wall, the nail acting on the wall and the wall acting back on the nail, but that wouldn't be balanced either.
The nails.
And what about the person itself? Alright, so actually here, technically speaking, this is getting into really nitty-gritty now, but if I strike a hammer into the wall, the hammer pushes back against me, my hand holds it, with my hand to hold it, I also have to have some grip on the ground, so there's friction that's there as well. So the other balance of FP would probably be friction between the shoes and the floor. And then the balance of FW pushing forward would be the structure backward.
Does that like vary based on how hard you push the nail into the wall?
Sure, absolutely. If you swing, if your push is harder after the collision occurs, yeah, then it would vary the amount. It would also vary the acceleration with which the hammer pops back towards your face. Yeah, it's an interesting question. Let me think about that further, because I'm wondering, like, yes, all things have a pair, but does it matter? It doesn't matter in this case because we're not looking at the wall. We're looking at the nail and the hammer. But had we looked at a free body diagram of the wall and a free body diagram of me as a person, for me, you'd see the friction, and for the wall, you would see some sort of a reaction from the wall being embedded into the ground. But then we get into the whole, then what is the wall connected to? The earth. The earth is the major body. So like you could continue this further and further out to every single thing that's connected. Like me pushing against here is now the floor stuck to the ground. The ground is now stuck to the earth. So in the end, it goes back to everything is technically connected to the earth in a sense. Does that kind of make sense there? But yeah, we'd have to do like 3 or 4 more free body diagrams to see all the other pairs of forces there. It's a great question, Valentina. One I was not thinking of at all. All right, so let's take a look at weight. Let's take a look at weight. And weight is a little bit different than mass. And here's what I need you to recognize. Weight is a function of gravity. Weight is a function of gravity. Remember, mass, we talked about the simple definition of mass. The simple definition is the amount of matter that makes up an object. Well, that's never going to change unless you physically lose or gain mass by exercising or by consuming food. Those are the 2 ways that you can lose or gain mass physically, right? You eat a burger, you gain mass. You exercise for an hour and a half or run around or whatever, or walk up and down Loyola flights, right? Enough times, you lose a couple calories. You try to at least. But the idea behind it, right, behind losing or gaining mass is by changing energy. This goes to Einstein. Einstein said, well, energy is really just mass. So by intaking a bunch of mass, you're intaking calories. That's why you have calories in the back of the label, which are a measurement of energy. So you literally are consuming more and more caloric intake and therefore gaining mass. But when you expend energy and you use energy to physically run, you are therefore losing that energy in the form of mass. So mass can be lost and gained only due to losing or gaining some sort of mass, whether it's an intake or an outtake, or an output, I should say. Weight, though, is very different. Weight is a function of your location more than a function of your object. So if I were to go to the moon, and I've discussed this with you guys already, the gravitational constant on the moon is about 1/6 of the Earth. So if I were to go to the moon, I would feel like I weigh 1/6 of my actual weight, because little g on the moon is only like 1.6. Okay, lowercase g is only around 1.6 on the moon, whereas on Earth it's around 9.8. So when we talk about weight of an object, the weight that you feel is a result of the gravitational field that you are immersed in. So if you change the gravitational field, you change your weight. Gravitational fields actually change not just from planet to planet, but based on elevation as well. Not significantly enough, but enough that if you were a real engineer or scientist, you would account for it. Meaning, if you're at the top of a mountain versus 2 or 3 miles below the Earth's surface, gravity is different in those two spots. As you get further from the center of the Earth, gravity weakens, actually. 9.8 becomes 9.79, 9.78. It gets lower and lower as you elevate further away. If you are closer to the center of the Earth, gravity is stronger toward the center of the Earth, which is why a lot of the planet's material is more dense as you get closer to the center, because it's got more of a pull toward it. Yes?
How do we figure out that gravity is 1/6?
Oh, that's a great question, actually. I don't know the original experiment, but I know that when we did set foot on the moon, data was absolutely taken. So you could drop an object in time of free fall and calculate it.
Yeah.
Right? Y equals y0 plus v0 t plus 1 of at squared. V0, y0, those things drop off. You physically have the height it falls, and you can time it. But I don't know, actually. It's a great question. Where was the first calculation of moon's gravity? I don't know.
But is there air resistance?
Does the moon have an atmosphere at all? Anyone know?
Sure.
I don't think the moon has an atmosphere.
No,
Okay.
I don't think so.
So I'm going to guess that there is no air resistance. Yeah.
Yeah.
But it does have gravity. So even if you jump and push off, you're going to get pulled back.
Yeah.
You know what I'm saying?
Yeah.
It's not like you could just jump and you would go forever in space. There's no air resistance. Gravity.
So the kinematic equations that are like ideal on Earth are like actually what goes on.
What do you mean?
So like the kinematic equations do like the air resistance.
Oh yeah, they'd be perfect for the moon. Yeah, actually, absolutely right. Yep. Very true.
We're like that would work.
So again, remember that your mass doesn't change, only your weight, right? Your mass doesn't change, only your weight. Let's look at a first example. All right, so our mass is 25 kilos. What is the magnitude of its weight on Earth? This is a quick plug and chug. What about on Jupiter, where the acceleration due to gravity is around 2.64 times that of Earth? So I'm going to go through this quickly because it's a plug and chug. So I've got mass given first as 25 kilograms. How do I know that's mass? Besides, it says an object's mass. I get that. But how do I know? Juliet? Good. The units. What would the units be if it were the object's weight? What would it be? In English system, it would be pounds, yes. But in SI units, what is weight measured in? Newtons. So let's jot that down if anything comes. Remember last class we talked about newtons as the unit of force? So if I talk about my weight, or if a problem says an object of 20 newtons, it's referring to the object's weight. If it says an object of 20 kilograms, it's referring to its mass. Absolutely changes your results of any problem if you mix them up. So really important that we get that weight is units of newtons and mass is units of kilograms. It's got to be memorized. Okay, you got to have that up here. It's one of the few units, by the way, mass, that has a prefix to it. Almost all of the units have no prefix. Right? Seconds is just seconds, not milliseconds, not megaseconds. Newtons are just newtons, not kilonewtons, just newtons. But the base unit for mass in physics is the kilogram. Kilogram is the base unit of mass. It's not like, oh, kilograms, so that's 1,000 grams. So when I see 25 kilograms, I should write 25,000 grams. This is one of the few times that you do have a prefix in the base unit. You follow what I'm getting at right now. You do not need to adjust this into grams. I know in chemistry a lot of the time things were in grams, right? Because you're measuring small things, and everything else was rated to grams. In physics, everything is really made to kilograms. Now, I shouldn't say everything. If you look at like quantum mechanics later on, you'll get into much smaller objects, and then you'll be talking about, remember AMUs, atomic mass units? stuff like that, you can use instead of grams or kilograms. But for macro physics, on a big scale, it is kilograms. Now, we are asked to find the magnitude of the weight. The magnitude of the weight. So we're looking for this, but we're really looking for this. Okay, it's magnitude. Magnitude simply means its value, again, without the direction included. Its value without the direction included. So if I'm looking for weight, I start by saying, okay, weight equals mass times gravity. So if I get weight in general, the mass of this object is 25 kilograms, and gravity is 9.8 meters per second squared. Okay, this is absolute value I'm looking at here. It doesn't really matter because I'm looking at a positive quantity here. When we get into free body diagrams and we look at direction in those, then the sign of negative or positive will matter. But for now, it doesn't matter. And I've been using 9.8. Sorry, not 9.81. So I'll get rid of the 1 there. So that'll give me the weight of this object on Earth. What does that come out to be as a number here? Yeah, give me a quick number so I don't have to wait. Thank you. 245? Even?
Yeah.
Thank you. Okay, so that's the weight of the object on the Earth. Which way does weight act again? Down. It acts down. So when we get into equations of motion, we're going to call weight usually a negative force. Sometimes we'll call down positive instead of negative, actually. And we'll talk about when that is. Pulley systems and stuff. Really help you a lot for AP Physics. If we get covering that now this year instead of next year, which I've been having to do a lot of in AP, I think we cover it this year, and it makes it a lot easier for next year. So we'll talk about when down is positive, and that's a weird scenario, but we'll get to that, I promise. So for now, because we're looking at the magnitude only, we're looking at only a positive value. Now, I go to Jupiter. How do things suddenly change? I can do two things. I can do it one way or another way. Give me a suggestion of how to approach this. Give me one way.
Can you multiply 9.8 times 2.64 times 25?
Yeah, so just pretty much change your gravitational constant by multiplying it by 2.64. Would everybody agree with that? So what's the quicker way to do it, though, to get a quicker answer, Jack?
Multiply 2.5 by 2.64.
Yeah, because technically, see, I kind of set you up there. Sorry, Caroline. It was one of those scenarios that you knew that was going to be an easier answer. So I could do this. I can multiply by 2.64, right, to now give me Jupiter. And inherently, what am I doing? I'm just taking this 2.64 and carrying it down. So I would multiply by 2.64 here, and then we can get the weight on Jupiter. Okay, so the weight on Jupiter is Earth's weight times 2.64. Okay, that'll turn out to be 646.8. I'm just doing it quickly. I have it written down here. Okay, and those are measured in newtons. So on Jupiter, 646.8. On the Earth, we're looking at 245. Clearly larger on Jupiter. Why? Jupiter is more
Dense.
Oh,
what is it?
it's more mass.
More, you're on the right track.
Wait.
Massive. It is, we need vocabulary, right? It is more massive. Jupiter is more massive. So Earth's weight is here, then we multiply by this number, and we get Jupiter's weight over here. Jupiter is more massive, it has a higher gravitational pull. You would feel like you weigh more on Jupiter. Jack?
If you're hypothetically 646 pounds,
Whatever, yeah.
on Jupiter, what would happen? Like,
Okay, let's talk. I was about to follow up. So, before I answer Jack's question, I'm going to pose a question for you. Here's my first question is, has anybody ever seen, there's a show called Dragon Ball Z? I maybe referenced this at any point. Come on, be honest. Anyone ever seen it? Somebody in the class has got it.
Hang on.
Okay. Goku, have you heard the name Goku before? Yeah. Guy's got yellow hair, it's all sticking up, right? Okay.
Yeah.
So I'm going to give you a little background on Dragon Ball Z. I love Dragon Ball Z. It's my favorite show ever. It's really good. It really is. So, anyway, one part of the show, there are these characters in the show. It's all about like saving the universe and these fighters and stuff. And they're training in the show, okay? And the main character, his name is Goku. He's training. He's trying to train so that he can fight against this like, evil lord called Frieza. And it's early on, this segment in the beginning of the very beginning of the show that happens. So if you watch like the first like 30 episodes, which are only like 20 minutes each, you'll cover what I'm talking about. Somewhere. So Goku is training, right? And here's here's what Goku's a really smart guy, also, good fighter but smart. So he realizes, you know what? If I could go to the planet and fight this evil lord on his planet, or wherever it is he's going to fight in, but train on a planet that has a much higher gravity, when I get to the new planet, everything will feel lighter to me. Think about it, right? So if I go to the moon today, if I walk to the moon, if I launch to the moon, and I pick up this marker on the moon, if this only weighs a half a pound, now it only weighs, what is that, a 12th of a pound. It's 6 times less weight on the moon than it is on the earth. So if I were to pick up, let's say, all right, for lifting weights, right? Dumbbell sizes. You look at pictures of Goku right now?
Yeah, I was seeing that.
Yeah. So you're lifting, say you're lifting a 15-pound dumbbell, and you go to the moon and you lift the same dumbbell, it's only going to feel like it weighs 2.5 pounds. It's going to feel like it's a sixth of its weight. So you as a person would suddenly feel a lot stronger. So in the show, Goku has somebody create a ship for him. By the way, they can travel at the speed of light. Like, a lot of physics is not true in the show, but this part is really cool. And the ship can simulate gravity. And what he does is, every day, he increases gravity by another G. So on day 1, it's 9.8. On day 2, it's 19.6. On day 3, it's 27, whatever it is. And he trains for like 1,000 days. And he also uses his time dilation, so he can train for 1,000 days, when in reality, it only is like 4 days that have actually gone by. That's called time dilation with speed of light. Anyway, so Goku trains until he gets to 1,000 times gravity, and then when he gets onto this planet, he like steps off the ship, and like a normal jump, which would be like this, he jumps 1,000 times higher suddenly. So he's this like super strong guy, which is really where the whole premise of the show starts, where he becomes like what's called a Super Saiyan, which is another level of strength. Anyway, my point is, what would happen, Jack, is exactly that. If you went to Jupiter, you'd feel weak, because Jupiter has a stronger gravity than Earth. But if you went to the moon, you'd feel strong, because gravity on the moon is less than the Earth. So it's relative to where you train. That makes sense? Long answer,
I
but
think I've seen something like this on Sesame Street.
it's on like Cartoon Network and stuff.
Like Grover was like trying to pick up a shot and he was like, oh, why?
Since your weight,
Let's listen.
since you are like 1/6 as well, are you able like to harness your energy because you're lighter as well?
So you're lighter, but your muscles are still exhibiting the same strength they had. So remember, what causes you to jump and walk are your muscles. So it's not the mass of your body or your weight at all. It's your muscles themselves. So when you jump, because you feel like you weigh less, your muscles are now lifting with the same force, but 1/6 of the weight. So you're going to go 6 times as far, or 6 times as high, or 6 times as fast, or whatever it may be for that
Further
time.
faster.
Okay?
What is it?
Jack.
For those like airplanes that like go 0G, how do they do that?
For airplanes, and when people like float and stuff,
Yeah.
they just do a free fall at the exact same rate of gravity. They free fall at 9.8 exactly. So that when they're falling, people suddenly feel weightless in there. We'll get into more of that when we get to like gravitational constants and gravitational motion of planets. Oh yeah, that's exactly what's happening there. There's a video by like OK Go, or what's the band that does the free falling? We talked about
I think it's them.
Okay,
Yeah,
go?
I think we talked about that.
Yeah, there's a music video, like a band that does everything, they're like floating. They actually do exactly that. They get in a plane, they take the plane, they slowly cruise to a certain height, and then they drop at the rate of 9.8. And everybody starts to float, and they're recording the video while floating. And they only got like 20 seconds at a time, and then they have to come out of the nosedive, go back up, and then drop again. And it takes them like a couple minutes to rise up, and only have 20 seconds to fall. And the pilot has to keep doing these nosedives over and over. That's how they record the video. It's really cool.
So stressful.
Say again? Absolutely dangerous, but the pilot's trained to do it. But it's not just a random person.
Ever do that?
Well, don't forget, so what happens is this. When they're about to pull out of the nosedive, they have an alarm go off and everybody straps in. They're near enough to something that they can pull a strap to them and strap in, and then once they're there, they start going up, they're strapped in. And then once they start to free fall, they feel it, they take the straps off and start floating, and then they record the video. But it was like over and over they had to do it because of the fact that they were just iterations of it. So here's a methodology I want you to consider, when solving all force problems of this chapter. And we're going to use this in coming chapters as well. So first, I recommend drawing a sketch. A sketch is different than a free body diagram. A sketch is a sketch of the whole scenario. Second, well, and if the scenario has multiple instances, like time 1, time 2, time 3, several things are happening, maybe several sketches along the way. 2, draw a free body diagram. I'm telling you now that you will never get full credit on a math problem on the test if you don't have a free body diagram. On the AP exam, you get credit for a free body diagram. It's the part 1 of any force problem will be draw a free body diagram of all the forces acting on the bullet, all the forces acting on the car, on the person, on the roller coaster car. Whatever it is you're analyzing, drawing all the forces acting on it. So step 2 is the most important step of all. It's the most important step. Now, you then want to look at all of the forces acting at angles. If a force acts at an angle, you want to break it into its components, like we did with velocity. So when VO was like this, we said, oh, VOX is VO cosine theta, and VOY is VO sine theta. Remember, we broke into components? So if I have an applied force at an angle, what does that really mean? It means that I'm pulling it to the right and I'm pulling up at the same time. So step number 3 is to break up any forces acting at an angle into its components, Fx and Fy, we're going to call them forces. Step 4. Step 4 is the part that gives you all of the math that you're going to use. Step 4 is this. Use Newton's second law. Always. Write that in big letters if you need to. Always. You're always going to apply F equals ma. Now, we're specifically going to apply it in the x direction and in the y direction. And we're going to do that separately, and there might be some overlap. But we're specifically going to apply F equals ma in as many directions as possible for a given problem. Now, if I looked at the pencil case again, right? I put the pencil case down on the desk. What forces did we say act on the pencil case right now? Gravity, which is the weight of the object.
The table is the force going up.
Good. And then table pushing back up. Are there any horizontal forces acting on this right now at all? Nothing's pushing left to right. So if I were to draw a free body diagram, it would only have arrows up and down, right? So when I use Newton's second law, would it be in the x direction there? No. It would be in the y. So Newton's second law is specific to each direction. It's a vector quantity. The direction absolutely matters. So when we write F equals ma, we're going to one time look in the x, and at another moment we're going to look in the y direction. Yes?
What if an object was just sitting there and there was a wall like directly on the side of it, but it's not really like this, like that?
Still only vertical forces. Remember, the only time you're going to exhibit a horizontal force is if there's some external force pushing it, or if it's on an incline. And we're going to get to inclines soon too. Inclines are a whole other question, a whole other ballgame. But inclines do have many different types of force, and we'll get to those. That would be the only other time. Yeah.
What if you you had your iPad propped up against something and is the wall exhibiting force on?
Oh, then it is for sure, absolutely. Because without the wall, what would it do?
Fall.
Fall. Well, would that fall without a wall next to it? No. So that's what I'm getting at.
Okay.
You know? If it's actually supporting you, then it would be a horizontal force pushing back. Like it was not supporting that when I placed it here. Okay? Technically, the ledge is slightly this way, so the markers don't fall off. So technically, you could say the wall is supporting it. But if I just move the eraser out a little bit towards you, now it's not in contact. The wall is still there. Okay? All right. And then finally, the last step, which is step 5, is to solve the equation that results from F equals ma. And we'll get to that in a moment so we can see that happening. Okay? So let's discuss this term. This term is called normal force. We already got into it, but I want to make sure that it's clear. So a normal force is a reaction force. It's a reaction. And it's always acting perpendicular to the surface. It's a surface force that acts perpendicular to it. So the pencil case has the normal force pushing back up on it. If I were to look at this inclined plane right here, and this object resting on it, when the object is at an angle, it's still on a surface, right? And since we said that the normal force is perpendicular to the surface, the normal force here is at an angle also. If I do this, then the normal force moves. Look at the normal force. It's literally changing. My hand is the vector showing the direction of the normal force. It's always perpendicular to the surface. So when the surface is flat, the normal force acts in the y direction, straight up. But when the surface is angled, the normal force acts at an angle. We'll get to inclined planes with that concept. Third example of normal force here. Third example. How is it possible for me, a mere weakling, to hold, really, I'm not a strong person, really, to be honest. So, how is it physically possible for me to hold this eraser here? Seems pretty easy because the eraser's not an acid, right? How is it possible?
The wall.
Wall's definitely doing something. Good idea. Jack?
The small force from your finger is pushing into the wall, and the force is kind of spread out. So, is that part of it, or no?
Good idea, though. I like you're getting at. You're like, hey, there's more grip. It's a bigger surface, right? That definitely affects things for sure. The bigger surface. That's not what's happening, though. What's preventing it? Like, okay, take a bigger object now, right? I mean, oh man, I don't want to screw anybody's things up. Here, can I use your backpack?
Yeah.
All right. I'm trying not to get dirty. All right. So we've got M's backpack here, right? And I'm holding it against the wall. Notice how much harder I have to apply force here? Can I do the same thing as the eraser? I can't, right? I literally can't. But if I push hard enough, and kind of at an angle it looks like, but I can do it horizontally, her backpack gets held to the wall. Why is that? Why is that? Think about it logically. What's keeping it there, George?
Maybe because the wall's pushing back on the bag, and like those two forces against each other are like keeping it in place.
So George is on the right track that the wall pushes back. So these two forces are balanced this way, George. But why isn't it falling down, George? Why isn't it falling down? Because remember, pushing this way doesn't affect down. It only affects left and right. Why is it falling down, Vin? The friction between the object and the wall. Well, it turns out that when you push against the wall pushes back. And that's called the normal force also. So this normal force pushing off the wall. And the greater the normal force, the more friction you're going to have. We're going to get to that concept of more normal force causes more friction in the next section. But think about this. If I push the wall has to push back. So when I push on this object, sure, the weight acts down, right? The weight pulls it down. But the normal force now is no longer pushing back up because it's not sitting on a surface. If I did this, now the normal force pushes back up. But there is no surface below pushing back up. The normal force comes out of the wall or is directed away from the wall. Okay? The normal force does not act up in this scenario. It acts horizontally out of the wall.
So is that scenario kind of like the static friction, but just like sideways?
It's static friction, and the friction acts upward. It's balancing gravity, which is pulling down.
Yeah.
It's just sideways. It's all rotated 90 degrees. Yep. So what I want to point out is that the normal force is a reaction from a surface that is always perpendicular to that surface. Normal means perpendicular, by the way. In math, later on, you're going to hear the word normal, and it physically means perpendicular. Good.
So is there always like a force acting on each side of the object or not necessarily?
Unless the object is in outer space and it's having nothing next to it, not touching anything, then yes, there'd always be something acting on it.
Like up, down, and horizontal?
No, not always both, but there's always some force acting on an object. There's got to be, yeah. Okay? All right, let's take a look at an example of this. Okay, let's look at an example of this. So, the first example says the following. If an object is at rest on a table, so we're looking at the pencil case right now. It's at rest. The mass of the pencil case or the object is 10 kilos, and you're trying to lift it with an upward force of 35 newtons. You're applying an upward force. Will it lift off the table? If not, what is the normal force from the table? So let's start this problem first with a diagram. A diagram is always nice. Before we even get to the free body diagram, I could start with a regular diagram if I want to draw a sketch. The sketch for this one is not that detailed. There it is. I mean, this is pretty much the sketch right here with some external force acting on it. Again, this is not my free body diagram. Okay, this is just a sketch of the scenario. That's it. That's all it is. And the question is, will it lift off the table? That's what we're trying to figure out. So now what I do is I draw a free body diagram of the object itself. What pulls all objects down? Gravity. So let's draw this as F sub G. Remember, the subscript is G. It's not a variable right now. It's a subscript. It's not like I'm taking F and multiplying it by 9.8. That is not what I'm doing here. This is a variable with a subscript. All of my forces are going to have subscripts. Every one of them will have a subscript. If they don't, it's usually just some external force applied. But even that, I usually put FP for a push or a pull. Now, we know that if this object is resting on a table, then the table must be pushing back against it. And the table pushes back against the object with what we call the normal force. So this is the current situation before I try to lift it. So right now, before I walk over to the pencil case, this is the scenario. Then as soon as I get here and I try to lift upward with a force, maybe it's not enough force to lift it off the ground. I mean, you've done that before. Have you ever gone to the gym? Well, I mean, maybe you've done it before, I don't know. But if you've gone to the gym and tried to lift like a really heavy dumbbell and you just can't lift it off the ground, if you have like a 100-pound dumbbell on the ground and you physically can't lift it, you can pull as hard as you want. It's not going to go anywhere. You might lift with 80 pounds, but it weighs 100, so it's not going to move. If you lift with 90 pounds, you're getting closer, but it's still not going to move, right? You have to apply at least 100 pounds in order to overcome the weight pulling down. So the applied force in this situation is also upward, and the way I like to draw those is with the second arrow. Okay, the second arrow is in the same exact direction. I stack my arrows. Some textbooks put them next to each other. I don't like doing that because by putting them next to each other, sometimes they look like they're going away at angles. But these are both vertical forces. You follow what I'm saying? Sometimes textbooks will put both forces acting upward parallel to each other. But when I draw a diagram, it's really tough to draw that. To draw two perfectly parallel vectors coming from this little dot. So I like to stack them. Either way is acceptable. So if you prefer the other way, that's fine as well. So these are the three forces acting though. So that's the question we're having here. Is 35 newtons enough for liftoff to happen? Is it enough for liftoff? What do you think?
Yeah.
You think so? Why?
Because 35, I think 35 newtons is equal to more than 10 kilograms.
That's a good question, actually. Well, we should be able to figure it out, shouldn't we?
Yeah.
Because we are given the mass, not the weight. We are given the mass. M in this problem is 10 kilograms. The applied force is given as 35 newtons. Gravity is 9.8 meters per second squared. So this is my arrangement right here. These are all of the given pieces of information. So I need to start by looking and asking myself, okay, what are all the forces acting? And to do this, I'm going to do it very slowly for the first problem. And then I'm going to pick up pace from problems going forward. So for this first problem, I start with Newton's second law. The sum of the forces in the y direction equal MAY. So that's my starting point right there. This symbol again means sum. The sum of. So what forces are acting positively in this problem? What forces are acting positively, Julia?
Normal force and push.
Pull, push, either one. Good. I would say pull. Pull that one. So those are both positive forces. I agree. And then there's one force acting negatively here. What do we call that force? Good. The force due to gravity. So I put a negative sign there. So this is my equation for Newton's second law. So for all problems this year in forces, we're going to start with F equals ma, always. Always starting with F equals ma. And then we're going to replace this with literally all the forces acting. Anything acting up or in the positive, we'll call positive. Anything acting down or in the negative, we'll call negative. So we don't need to label G as negative 9.8 anymore. Do you remember last chapter? With projectile motion, this was always negative 9.8. Think about it logically. This already has a negative sign, doesn't it, right here? So when I replace FG with its formula, what was the formula for FG a slide ago? Or 2 slides ago, what was the formula for FG? FG is simply?
FG equals mg.
Equals mg. So when I replace that with the formula mg, the equation becomes this. That's the equation now. I'm only replacing FG with mg. And look, the negative sign is already there. So don't double negative by accident. So in this chapter, and going forward, G is going to be 9.81. It's only with projectile motion that we need the negative sign for G. For all other topics this year, we're going to see G being positive 9.81, which is why on your formula sheet it's not listed as negative. It's listed as positive 9.81 actually, or positive 9.8. But in projectile motion, we need to know that it decelerates you. It pulls you down, which is why it's a negative quantity. It's pulling you down to the ground. Good.
Why did you replace it with energy?
Because that's the formula for it. If you go back a couple slides, we wrote down that the weight of an object is equal to the mass of the object times the gravitational constant on Earth. So this replaces Fg. Just literally swipe up 2 slides. It's a formula. It's nothing more than that. It's just replacing the formula given. And we're going to have a couple of mini formulas in this chapter that are going to replace specific types of forces, and this is one of them. This formula is going to become pretty much second nature to you. When you're asked to find the weight of an object, mg, automatically, mg. Some teachers actually, and you can do this if you want, some teachers don't label this as fg, they just label it mg. And you can do that if you'd like, that's fine with me. If you remember better, say, call the weight mg every time. I write it as fg because I like to think of this as a force due to gravity, and then I remember that fg is just mg. And I actually think that this is on your formula sheet. I think this formula here, it might be, I think it is actually on your formula sheet. If it's not, it's okay, you'll memorize it, I promise. Now, the problem is still not over because we still don't know what the answer is. It says, will it lift off the table, right? Will it lift off? Let's ask this question now. If I lift this off the table, follow me please, what's the normal force then? What's the normal force, Nora?
0.
0. Why, Nora?
Because it's not touching the table and you know it's not exerting force down on the table.
Yeah, it's not exerting a force on the table. So can the table exert a force against it? Physically can't. There's no contact. It's a contact force. The normal force is always a contact force and not a distance force. So if it's not on the table, there can't be a normal force. So the question really becomes this. If I can lift it off the table, then this drops off. You with me right now? If I can lift it off. But if I cannot, I gotta use your thing again, sorry, I'm gonna zip it. If I cannot, but I apply, let's say that the weight of this object is 2 pounds, US pounds, okay, 2 pounds. And if I were to apply a force of a half a pound, can't get it. A pound, I still can't get it. But when I reach 2 pounds, it just starts to come off the table, right? So if I apply a pound and a half, how much does the table have left to cover?
0.5.
Only half a pound. Again, think about this for a second. This weighs 2 pounds, this weighs 2 pounds, and I lift with a pound and a half. How much is left for the table to resist is only a half a pound. Make it easier. Call it 5 pounds. If I lift with 4 and it doesn't lift off, what's left for the table? Only 1 pound is left behind. So really, if I don't lift it off the table, we'll still have normal force. So we'll have to calculate Fn and read the problem. It says, will it lift off the table? Will it lift off the table? If not, if it doesn't lift off the table, what is the normal force? And that's the scenario that we're probably going to be in, where I try to lift it, but it's not enough strength. So how will I be able to tell if my lift force up will overcome the weight of the object pulling down? How can I figure it out? Physically, how can I figure it out? I don't know.
By like trying to pick it up.
Okay, physically by trying to pick it up, yeah. If it's a real life scenario, by trying to pick it up. In this problem, though, how would I numerically determine if my applied force exceeds the weight of the object?
You would see if the left side is greater than the right side.
You're on the right track. I get what you're saying, George, but not exactly. You're on the right track, though. Again, listen to my words. Ready? How can I figure out if my applied force exceeds gravity, exceeds the weight of the object? Good.
Just greater than if the applied force is greater than the gravity.
Yeah, so look, don't we have the applied force? So what should we probably calculate in this problem before we even do anything? The weight of the object. If this number is more than Fg, it's definitely going to lift off. And now the problem doesn't have normal force anymore because I've lifted it off the table. Let's calculate Fg on the side over here. Fg is mass times gravity, which is 10 times 9.8. So the weight of this object is 98 newtons. Give me another minute of your time, please. The weight of the object is 98 newtons. But what was my applied force? Only 35. I am weak. I am not strong enough to lift this off the ground. I only applied 35 newtons, and yet it weighs 98. So is it going to move off the table? If I'm not applying enough force, will it move? So what's going to happen to the acceleration of this object? What would the acceleration be if it's not moving? That would be 0. So based on this statement, take a look. Because it's not moving, this goes to 0. Again, because it's not moving, MAY is really 0. It's not lifting off. But, if it were lifting off, then, let's take a look again, take a look up here, then this would be 0. If it does lift off the table, then the table can't provide a normal force anymore, so this cannot be here. And if it does lift off the table, what's the only way you can gain velocity? By having acceleration. So it turns out that if it did lift off the table, this would not be 0, and we would have to calculate acceleration. But if it doesn't lift off the table, then it is 0, and now we have to calculate the normal force. So let's solve for Fn. Let's solve for Fn. Fn will equal, I'm going to add mg over, I'm going to subtract fp over. That'll be mg minus fp. And that's exactly what you guys gave me as an answer before. When I said, hey, this pencil case weighs 5 pounds, and I lift up with 4, what's left of the table? You all said 1, right? How'd you get the answer? You subtracted the 2? Look, it's exactly that. How much does it weigh? 98. That goes in right here. How much do you pull up with? 35. That goes in right here. So it weighs 98. You pull up with 35. Not enough to lift it. Therefore, there's got to be some normal force left, which is what's left over. So my normal force would be the weight of the object minus the applied force I give it, which in this case is 63 newtons. Now, I want you, listen carefully, I want you to look at, hold on. Yeah, okay. I want you to look at we're going to do example 3 together. I want you to look at example 4. Okay, I want you to look at example 4. You had homework due today, 4.1 to 4.5?
Yeah.
Make sure that's in, obviously. If it were me, until Thursday, I'd probably start the problem set for 4 and 4.5 or work on my project a little bit. But I want you to do example 4 in the notes. And it's very similar, but what do you think is going to happen in example 4? Yeah, this applied force will exceed the weight, and therefore it will lift off the table and will have acceleration. This will not be 0. Instead, this will be 0 if it lifts off the table. Okay? All right, guys, go. Have a good day. Thank you. Example 3 says, a small object is stacked on top of a larger object, and they are both on top of a table. If the masses are 5 kilograms and 15 kilograms, what is the normal force acting on the object? Now, in these problems, when they say small object and larger object, the assumption has to be that we're referring to its mass and not its volume. Is that clear? Okay, because I understand, trust me, like this box here could be a really big object, but if there's nothing in it, the mass is very light, right? And this could be a very small object, but this could be heavier than this entire box if this box were empty. So in physics problems, when they talk about large and small objects, and you're talking about forces and mass, they're referring to the mass. So 5 is the smaller object and 15 is the larger. Is that clear what's happening here? Okay, it's not about volume, we're referring to mass. Regina, sorry, you got a hand up.
I was gonna say, for the one before, I did a different way and I got the same answer.
Can you tell me?
I don't know what I did. So I found the force, I did mass times, I found force was 100 and the mass I put in 8, got 12.5, and then I subtracted gravity to get 2.69.
Subtracted gravity. You subtracted 9.81?
Yeah.
No, you just got lucky then that it worked, so yeah. Gravity has to always be multiplied by the value of m to give you the weight. I could look at your work later and see, Regina, just to see why it worked out. And you're saying you got exactly the same answer, like,
2.69.
and that's what we had, 2.69?
0.7.
Yeah, so it's possible it just happened to happen that way, or maybe there's something you did that made it work. I can look at that separately, yeah, I'm happy to. So we've got these two objects stacked, 5 kilos and 15 kilos. Now, I'm not going to really push on the quiz much about this, but going forward, it needs to be done the right way. You can't label three-body diagrams in the whole diagram. Okay? Some of you did on the quiz. I'm not going to take off right now. Okay? I walked as I was going around, but I wasn't going to say anything. You want to draw them separately. Always draw them separately. A free body diagram is all the forces acting on a single object. So because we have two objects here, like you did on the quiz, you draw two separate points. This is object 1, this is object 2. Okay, we draw them physically separately so the vectors don't overlap. Now, object, let's say this is small and this is large. We'll go small here and large here. And I would personally always denote which one I'm labeling so I know which forces are acting on which object. So small and large. The small is on top. What is acting on that small object on top? What's physically acting on it? Give me something. Gravity. So the weight of the object is absolutely acting on it. So let's call that FG1. Call it FGS for small and FGL for large. Or A and B is fine, or 1 and 2 is fine. Whatever subscript you choose, just be consistent throughout the problem. If you call it A and B or 1 and 2, it doesn't matter. Large, small, Joe, Chris, it makes no difference if you call these names of objects, but be consistent, that's all. Jack.
Another force is coming from the box underneath and I guess the table as well, going upwards.
But what's actually acting on the small object? Is the table actually touching and acting on it?
No, it's the
So what is it
box.
then? Just the box below. So let's listen to what Jack just said there. So there's a normal force acting on this object from the object beneath it. The table only acts on the big object. The table pushes on the big object, but the big object pushes up on the small object. So Fn1, I'm calling it 1 right now. Why do you think I'm using 1? Because there's going to be 2. That's the only time I denote 1 or 2 or A or B is if there are multiple parts. So the bigger box supports the smaller box with a normal force coming from the bigger box. So for example, literally look over here. This object is currently supported by the table, right? When I place this box on top, sure, the table is now supporting both of them, and I get that. But the table is only physically supporting this one right now, which this one in turn supports this one. If the top of this box was not structurally sound, what would happen is this would literally fall through the upper box or break through it. Now, the table might stop it, it breaks through and falls to the bottom, and then the table stops it, right? But the upper box is what's physically supporting the lower box is what's physically supporting the upper box here. That's what Fn1 is. Fn1 is the reaction from the larger box pushing up on the smaller one. You got a hand up.
Will there ever be a time where there won't be I'm confused on normal force.
So normal force always exists when you have an object against a surface. So if I push against the wall, if a roller coaster is going through a loop-de-loop, when your body gets sucked to the seat, when this pencil case sits on the table. So in all of these scenarios where it's resting on a surface, there's going to be some form of normal force. Now, could that normal force eventually be 0? Sure, and we saw that in the other example, if you pull up on it with enough force. Or the roller coaster problem. There's a type of that problem where there's an instant where you feel weightless for a moment, and we'll get to where that is. So the normal force is a little bit confusing, but for now, I want you to think when it's on or against the surface, normal force reacts from that surface. Okay, so what is the surface that the small object rests on? It's the large object. What is the surface the large object rests on? It's the table, or whatever it says here. Okay?
Another question. When you draw your arrows, does it matter if it's like shorter or longer?
So that's a great question. You know, I've never cared about the vector length. But Mr. Donachek the other day said to me that you probably should indicate which is larger or smaller with the length. The problem is, I don't know Fn1 right now. I don't know the value of it. So I can't logically illustrate this. But on an AP exam, if you're told the upward force is 200, the downward force is 20, you should respectively make the upward force longer if you know the values. But I don't know the values, so for here it doesn't matter. But if you do know them, it is understood on an AP exam that you should draw them proportional to the number given. Okay, it's not going to be perfect, obviously. You don't have a rule or anything like that, but generally speaking, okay? Good question. Lower mass. What's acting on the lower mass? What do we got? More, give me something.
G,
FG1?
yeah,
Why?
because it's gravity.
So what is FG1 in your mind again?
It's still the gravitational force
Of?
of the larger body.
So we can call that FG1, even though we called the other one FG1?
I guess two.
Yeah, I guess 2, right? So I had to stop more there because you can't call the other one FG1 if we're calling that one FG1. Now, here's the thing, Justin.
Doesn't the 5 kilogram also put?
The upper mass, Vinny was seeing it too, the upper mass also pushes down on the lower mass. So it turns out that it's not just FG2. FG2 is the weight of this object pulling down on the table surface, or on itself really. But the upper mass also pushes down on the lower mass. So it turns out, and that's why I was giving you that kind of weird question there, it turns out that FG1 also acts on this mass. Think about it. Really think about it for a second. If your hand is here and you put an object on it, what's acting on your hand? The weight of this object. Think about the dumbbell situation in the gym we talked about. If you literally are able to lift a dumbbell, you must be able to lift up with a force equal to the weight of that dumbbell. If this is a dumbbell that weighs 5 pounds, I need to lift up with 5 pounds. It's not going to work if you can't. So this problem here of the 5 kilogram on top of the 15, the 5 kilogram pushes down on the 15. Think about it. If you ever unroll a poster, who likes to put posters in their room? It's a big thing I did when I was younger. All right. So posters aren't a good example. So that was going to be an easy one. What?
I feel like soccer jerseys.
All right, on your wall you put a soccer jersey. All right, so let's hypothetically say, oh great, okay, this is perfect. Soccer jersey, right? Your soccer jersey's all wrinkled. You can't put that up on the wall if it's wrinkled. That looks terrible. So what do you have to do? And when you iron, what do? You apply a force downward on the shirt, correct? And that flattens the shirt. I was going to use a poster. When you get a poster, it's always rolled up in the tube, right? You know what I'm talking about? And when you want a poster to look nice on the wall, you lay it out. And when I was a kid, I always did this. I put textbooks on top of it. And you literally lay out all the textbooks on top of the poster and let it sit on a table for like 4 or 5 days, and it will flatten out, close to flatten out. Because what are you doing? You're applying a downward force on the poster with the textbooks. It's literally squishing it. That's what's happening here. The 5 kilogram mass is applying a downward force on the 15 kilogram mass. So therefore, we have a second force acting downward. Could we draw this force from the top acting down, pointing to this? Sure we could. I'm going to show you what I mean. I could draw this force like this instead. And some people like to do that to show that it's coming from the top of the object, pushing down on it. That's fine. I personally like to draw all my vectors on one side or the other. So I don't like the direction being different on the top. So any vectors I draw on the top, I like to draw upward. So that's why I put FG1 below it, but it shows that both are pulling down. Pulling down, I should say, and this one is pushing down. See the difference? The weight of the bottom object is pulling on it. The weight of the top object is pushing down on the bottom object. So this is a force of push coming down on it. This, though, gravity is physically pulling you down. Pull and push are very different, right? We know that? This is a push. This is a pull. Okay, very different things. George.
So when you're putting like your books on your poster, is the poster pushing back up on the books, or like the table under the?
That's a great question, George. The table is pushing the poster is pushing the books.
Okay.
But the table is enough to support both, which we're going to see now in this one. Okay? Yeah.
Is FG1 smaller than FG2 because we know the mass?
Absolutely, absolutely. So for that one, we can indicate the length of the vectors. You hear the question there? We know FG1 is definitely smaller than FG2, for sure. Because FG1 is the weight of the small object. Yep, absolutely. Even though we didn't calculate it yet, we know that for sure. Now, what is holding both of these objects up? Both of them, Natalia?
The table, so we FN2.
Very good, Natalia. Oh, the table, which is FN2. Oops, I did not mean to use red, sorry. The table, which is FN2. Now, could you tell me something else? Which is going to be bigger, FN2 or FN1? Which is going to be bigger? We're not doing any math. Which is bigger, Jack?
FN2.
Why?
Because it's holding more weight.
It's holding both, more weight. So FN2 vector could be drawn bigger than FN1 if you want to be precise with your vector length, okay? But we know already that Fn2 is going to support both. Now, in this problem, is anything moving? Any motion at all? No, right? So if there's no motion in the problem, and we're talking about an object that's on a surface resting, what can we assume for this problem?
No FP.
No what?
No FP.
Good. No applied force. What
No
else?
acceleration.
And no acceleration. There's no applied force here, which is why it's not accelerating upward, no FP, but there's no acceleration because we know that these objects are at rest. So when I write my equation of motion, I write F net equals MA, and it's M1 first. So we only look at the first object, and we only look at its free body diagram first. It's the first time you're seeing multiple objects, if I'm going through it slowly. So you only look at the first objects first, which means that this F net is Fn1 acting up, and that's coming from right here, and then minus Fg1, which is pulling down on it. And that's going to equal 0, because again, there's no acceleration for the first or the smaller object. Remember, it's got a normal force pushing up on it from the bigger object. It's got its weight pulling down. Normal force is positive, weight is negative. Up versus down. Positive versus negative. So from this, we can find the normal force, right? Because we know Fg1. Fg1 is calculable. I don't know if that's the right word. You can calculate Fg1. And that's the formula for Fg. Right? Fg equals mg. That one, again, I said it last class, I'll say it again. You will memorize that. I'm telling you now, I guarantee you 100%, you will memorize that Fg equals mg. If not, I can't recall, maybe I'll check actually while we're here. Is it on your formula sheet? It is not. It is not on your formula sheet for the AP exam. So you know what? You will definitely memorize it. Okay? Fg is always mg. I'm putting a 1 here because I'm talking about the mass of the first object. So Fn1 is simply equal to m1g. And that makes sense logically. Here's how I would read this. If you want to write this in words and you're not understanding it or seeing it right away, I would recommend that. Here's what I'm seeing. Fn1, aka the force upward from the bigger box, is equal to m1g, aka the weight of the upper box. So the bigger box, which is the bigger cardboard box here, its normal force pushing up is only balancing the weight of this object, right there. This object's weight pushing down is balanced by the normal force pushing up. And that's what the statement says. That's why it's important that we look at variables also, not just plugging numbers. This literally says the force pushing up from the big box equals the weight of the small box. That's what that statement says right there. Now we plug in numbers. 5 times 9.8, 40 something, right? 49. Fn1 is 49 newtons. Okay, 5 times 9.8 is what that number is. Because M1 was 5, smaller object. How about M2? Can somebody give me the equation for M2? The upper mass, or sorry, the heavier mass, I should say. Not the upper one, the heavier one. Jack, go ahead, take a stab at it.
Not exactly sure.
It's okay.
M2, you would write down Fn2 equals M2 G.
Close, Jack. Give me the, before you solve it, I want the governing equation from the very beginning. Like, I know that this is true right away, right?
Yeah.
I start with this always. So start with that and now fill in the blanks.
Okay, so Fn2 minus F1 plus Fg1 plus Fg2.
And I'm going to write it like this. I like what you're saying. That's fine. Keep going.
Okay, equals M2A.
Which is?
0.
Okay, very good, Jack. So Jack did something which is fine. He said Fn2 minus the sum of these, which you can do. But then you would just distribute the negative anyway, wouldn't you?
Yeah.
So I'm just going to write them both as negative because they're both acting down. I like to just look at diagrams. I stare at my free body diagram and I say, what's up? What's up? What's up is Fn2, so that's positive. What's down are these two, so those two are both negative. Okay, and I always do this way. I just literally list what I see in my free body diagram. Now, what is known? These values are both known. We know the weight of both objects. And if I were to solve this, right, this is what it looks like next. I'm just replacing FG with its formula. And then I'm solving for Fn2. Can somebody make a statement in their own words that illustrates this last line of the equation? What could that statement be, Christina?
The normal force on the other object is equal to or balanced with the weight of gravity pushing down the object.
Good. Both, good. So the normal force acting up from the table, let's say, because we know that that's what this is equal to the weight of both objects. And that is logical. Look at the boxes. They're not falling right now. Why not? Because the countertop supports both of their weights, really. And that's what the statement says in the end. The countertop, Fn2, is equal to the weight of both of these objects, or the force provided by that countertop. And that's what we see in this equation. So this number will clearly be greater. Okay, M1G we know is already 49. And then if we add FG or M2G, we get 49 and 147, right? Yeah, 49 and 147, totaling 196. Okay, 196. And that's logical that that answer was greater. We saw that happening already, that this value would be greater than this value because it supports multiple objects. Multiple objects. General questions or specific questions on this example I'm talking about. This is the first multi-mass system we've really looked at, right? When we do that, the key, if you want to write it down, is to draw both free body diagrams separately. That is the key to this problem. Draw them separately, analyze them separately. There may come a time where we develop what's called a system of equations. We've done that already. And we had, if you remember from projectile motion, our linking variable is time and initial velocity and the initial angle. Those are the three things that carry over in both the x and y direction. It's going to happen here also. Think about the quiz problem you had today. Remember the one with the rope? That rope, we're going to get into tension soon. Okay, we're going to talk about that a little bit. But that rope that's acting over that pulley system right there in that problem, that rope is applied to both of those masses. So that's the variable that can go in both equations, Ft in that problem. Okay, we're going to see that more in a little bit. I asked you at home to look at, how does this problem differ from the one that we ended class with? Because it looks very, very similar, right? Jack, what do you think?
So since Fp is greater than Fp, the box is lifted up, so Fn equals 0.
Very good. That is the statement. Very good. Well stated, Jack. Fp, the applied force upward in this problem, is 100 newtons. It turns out that the weight is only, 8 times 9.8, 78.4 newtons. That's the weight acting down on this object. So clearly, if the applied force upward is more than the weight of the pencil case, it will lift off the table. And when it lifts off the table, there is no longer a normal force in the problem. Okay, therefore, Fn equals 0. And we can follow up by saying, therefore, the acceleration does not equal 0. These are the keys to this problem. Because the vertical force applied is greater than gravity, it must accelerate. Why must it accelerate? Why must it accelerate? I just said because the force upward is greater than gravity, but why must it physically accelerate?
Because it's angular velocity is 0.
Yes, the current velocity is 0. The current velocity is 0. If I literally move it at all, I'm giving it velocity, aren't I? And to go from 0 velocity to some other velocity, you must have acceleration. That's the kinematic answer to that question. The dynamic answer, forces, is simply, hey, the forces aren't balanced, right? If the forces aren't balanced, there must be an acceleration. So if the upward force is more than the downward force, it must accelerate upward. What if the downward force is more than the upward force?
Could be negative acceleration.
Yeah, which is this, right? downward force is gravity. As soon as I let go, the only upward force acting on it is air resistance, which is negligible. It's pretty much nothing in this problem. It's not a lot at all. So the downward force exceeds the upward force of air resistance, and therefore it accelerates downward. So either way, if there's an imbalance of forces, there must be acceleration. So for this problem, my free body diagram is FP upward, FG downward, and then we had Fn, which we eventually realized that went to 0. But with the free body diagram, I would probably start by drawing Fn in the diagram anyway, because we don't know if Fn exists in the beginning of this problem. Once we recognize that Fp is more than Fg and it lifts off the table, then we can cross off Fn. But in the free body diagram, you still want to include it because it's like one of those, ooh, that could be a force there. And that's going to happen a lot with Fn. Where you start by drawing it in your free body diagram, and then you may not have an Fn value. It may become 0.
Does it matter if you put the force to pull above or below?
Doesn't matter, no. Yeah, either way. As long as the vectors are both collinear, or both acting upward in that case, you're fine. Okay? Now, what does my equation become as a result? I literally use sum of the forces equals ma. Right? F net equals ma. What's acting up is Fp. What's acting down is Fg. So again, and I'll put a little y symbol because it's in the y direction. But there's no x going on at all in this problem. There's no horizontal force, nor is there horizontal motion. So although I'm writing F net in the y direction equals may, I don't need the y as much in this problem. But in a moment, we're going to look at problems that involve both x and y directions. So we're going to have to specify which direction we're looking at. Here, though, I'm only looking vertically. Anything acting up is positive, anything acting down is negative. Now, there's going to come a time where I'm going to switch those things. Where I'm going to say down is now positive and up is now negative. Okay, so get that in your head already. I'm not going to do it yet. We're going to do it in a few problems from now. Where down is going to be considered positive, or I'm just going to change it up a little bit so you can think differently, especially when we have systems that are connected with ropes over pulleys. Because when this one moves down, this one moves up. Imagine a pulley system, just so you're aware of what I'm saying. Imagine a pulley system like this with an object on each end. If one object is heavier than the other, it will move. We assume no friction right now. We'll get to friction later. But if they're the same weight, they're going to be balanced. They're going to stay. And they'd actually be level if they're the same weight. But if one of these is greater than the other in weight, it's got to rotate. So already, if this one rotates down, this one rotates up. If this one rotates down, this one rotates up. So the motion is either clockwise or counterclockwise. So in those problems, we might start looking at our up and down in different directions. And we'll get to that when we get there. Okay, not involved for this problem, really. So the final answer here is just going to be that AY equals FP minus FG all over M. And our goal is to find the acceleration, right? We're looking here. It says, if so, if it does lift off the table, with what acceleration? We don't have to worry about the second part, right? We don't have to worry about that part. If not, what is the normal force? Because it does move off the table, so normal force is 0 for sure. So we're answering what's highlighted in red. What does A become as an answer for this? What does A become? Jack, go ahead.
2.7.
Good. Thank you, Jack. 2.7. Okay? 2.7 meters per second squared. And you're going to notice more and more that I'm not going to do the tedious math in front of you. I'm going to allow you to recognize what you need to do. This is 100 minus 78.4, all divided by the mass. Mass is 8. Okay, all divided by 8. So our answer validates our statement. Acceleration is positive because the upward force exceeds the downward force. The answer validates our statement from earlier. Okay, so let's go back now, and let's go back to look at example 3. Let's look at example 5. This is where the bonus comes into play. I said I was going to give you guys an extra credit. This is the first extra credit opportunity of the year, actually. And the way I do extra credit is if you do it, you either get a 1, a 2, or a 3. Well, 1 means you did it, but really didn't do it that well. But I give you some points for doing it. A 2 means you did it, but the explanation is like, eh. A 3 means you did it, and your explanation is really good. And 1, 2, or 3 are the amount of points that give us a bonus and goes on your test. So if you want to do the bonus for this, I'll explain in a moment what you can do. Okay? We'll do the problem first, then we'll talk about the bonus. A person rides an elevator. Well, it's rare that I get bonuses, by the way. It's like 2 or 3 times all year. Person rides an elevator while standing on a spring scale. If you don't know what a spring scale is, well, first, if you don't know what a spring scale is or an analog scale, you're all probably used to digital scales. What's an analog scale or a spring scale?
Well, I'm just assuming it's like a step on a scale and measures like the tension and then like converts that to a weight.
Very good, Jack. Well explained. Do you know what it looks like physically? Have you ever seen it before? What a spring scale, how the reader would look on that?
It looks like a dial.
Yeah, very good. It's like a dial. Okay, so if you think about these old scales, the new ones that are digital, they work with a little electric sensor. It also senses the compression. It takes that little electrical signal, converts it to a value, and you get your weight. But an analog scale, you would literally have a little dial, right? It would go like this. Right? It's like when you measure voltage on the old voltmeters. Voltage coming out of the wall literally spikes. Or those like sound meters you have at like basketball games where they show the sound going up, it's measuring decibel levels. This is an analog scale. So as you step on the scale, it does this, right? It goes, and it rests at where your weight is. Now, if somebody else suddenly stepped on the scale, it would go up. If you partially stepped off the scale with 1 foot, it would go down. So if you use an analog scale on an elevator, you can see a fluctuation in weight based on the motion of the elevator. And we're going to talk about it here, but your extra credit is going to be to do exactly this, to go on an elevator with an analog scale, which is going to be tough to get one, I know that. If you have a digital scale, it'll work, but sometimes it doesn't, because the digital scale, it waits for it to hone in on a value. Have you used a digital scale before? When you step on it, it like fluctuates until it finds your value, and then it blinks 3 times. Okay? So yeah, you're gonna have to be awkward as anything and be on your elevator with a scale, and you have to record it too for the extra credit. Yeah. So I'll get into it in a second. So, is she laughing or crying? Yeah. And when people come by, you gotta say, I'm doing a physics project. And they're like, no problem, no problem. Oh, then you gotta find an elevator somewhere. You can use an elevator anywhere, any elevator will work. I don't have the key, so if you want to go get the key, you can. I don't use that elevator. If you can get the key somewhere and somebody's willing to lend it to you and you want to do it, but I would recommend you do it somewhere privately, because then you also need to bring a scale in.
For the scale, is it like the really big one that's like heavy and stuff?
No, you can get one that's like, it's like the normal size of a normal scale, except it just has a dial on it. You can borrow it from a friend or family member. You can put someone else if you don't want to put your own weight. I don't care. Any object. It doesn't matter what the object is.
So, are we going to stand with the scale in the elevator?
Or somebody else can, and then you could record the reading. Well, the recording needs to have somebody or something on it so I can see it, and then the actual analog. And then you have to explain the answers. And it's a video submission, yeah. I'm going to get into it. Give me a second. I want to go over the problem. All right, let's get into this problem and we'll talk more. So here's the question. The question says the following. What does the elevator or the scale read if, in this case, there's acceleration upward? What does the scale read if there's acceleration upward? That's the main problem that's posed here. So we're told that the person's mass is 10, so let's start writing stuff down. The mass is 10 kilograms. The acceleration is upward, so I'm going to call that a positive. And you know g is 9.81 meters, or 9.8 meters per second squared. Those are the 3 things that we know. And we're going to attack the first problem first. Okay, we're going to attack this problem. What does the scale read if the person's mass is this and accelerating up? We'll get to the second problem in a moment. Okay. So here's the 3 givens: mass, acceleration, and g. If I were to look at this problem now, and I were to draw a free body diagram of the person, let's put a dot here. On the left, I'm going to draw a sketch first. Elevator, elevator cable, scale, person. Okay, here's my sketch. This is not my free body diagram, this is my sketch. Now, the elevator pulls up or down on the object or on the elevator cart, which in turn affects your body's motion. And you know this, whether you realize it or not. When you go on an elevator, there are moments where you feel kind of weightless. Not weightless, but you feel like you weigh less. And there are other times where your legs feel a lot of stress. Suddenly you're like, oh my gosh, all that force on my legs. And we're going to discuss why that is, and you're going to prove this in your extra credit. So mathematically here, I'm drawing a free body diagram of the person, okay, of the person. Not the scale, not the elevator, but the person. Now, what acts down is the person's weight, and that always acts down. Because the person is resting on a surface, what acts up also? What is it? Normal force, because it's acting, again, it's resting on a surface. And that's all it's acting on this. What provides Fn to the person? I want a direct answer, not an indirect answer. A direct answer. Justin. The scale. Very good. Not the elevator card. What provides Fn on the scale? The elevator card itself. The person puts weight on the scale. Weight on the scale. So remember, this is very similar to the problem we just did with two stacked objects, right? But we are really concerned with what the scale is going to read, which is very difficult because nowhere do we say we have a reading for the scale. But here is the thing. The way a scale works is it's literally showing you the normal force pushing back. So let's write down in big letters that the scale reading is the normal force. Again, the scale reading, and this is for all problems, I'm guaranteeing you 100% on an AP exam, there will be a problem involving a scale. It is on every single one. Okay, you will have it on my next test for sure. A scale reading tells you the normal force. So in this problem, it says, what does the scale read? So what are we really asking? What is the normal force? What is the normal force? Now, you might think, by looking at this, well, look, oh, Mr. Howell, we've got normal force up, we've got the weight down, they're balanced, so maybe just the normal force equals the weight. But that would assume that the net force equals 0. When does the net force equal 0? Only when, yeah, when you're at rest, when acceleration is 0, or you're at a constant velocity. Give me one more minute. In this problem, acceleration is upward. So here's what I'd like you to do. I'll give you the governing, and I want you to finish it. This is the governing right here. This is the next line. Okay, this is literally our equation. And our goal is to figure out Fn. So let's move Fg over. Let's figure out Fn. And then I want you to look at the second part of the problem. Okay, I'll get more into the extra credit, I guess, on Monday, unfortunately. Okay, maybe I can even write it up and send it to you if you want to do it with me. Okay, have a good weekend, guys. We'll see you all on Monday. Enjoy your field trip. I know you're meeting now, right? Yeah? Have a good time. We got to this stage right here where we said, and we were kind of rushing again, if you remember, where we said that the sum of the forces acting on the person, right, on the person equals MA. And we're only looking vertically here, there's nothing moving horizontally. So we have the normal force. Oh, somebody else jump on accidentally? That happens times. It must be another teacher. When another teacher does that, it automatically overrides. That's all I'm going to say. Usually it puts code up for your name. So it's the normal force pushing up from the scale, and then the weight of the person pulling down on the scale. And that equals MA. The reason we have A here is because we're told that the elevator is accelerating upward. And again, this was where that extra credit came in. What do you feel like when the elevator accelerates upward? And think about that moment when it starts to rush and push up on your legs. Guys.
You feel heavier because there's more normal force.
Yeah, you feel heavy. That was rhetorical, by the way. But yes, you feel heavier. You do. I appreciate. No, good. I appreciate the answer. You feel heavier when you accelerate upward. What about when you accelerate downward?
You feel weight.
Yeah, you feel weightless, exactly. But you feel like you weigh less. Weightless. We're going to talk about right at the end of this problem.
Yeah.
Weightless is a very unique circumstance, and it's going to involve a specific acceleration. So let's quickly get to the end of the problem so we can see it. And I asked you guys to look at this. I said, you should probably finish this on your own, but just so you see the answer itself. So we've got Fn minus mg equals ma. And again, right away, whenever I see Fg as the weight of an object, I replace it with mg in my formula. It's mass times gravity. So Fn, again, is the scale reading. So the scale reading is going to be ma plus mg. So let's look at the logic behind this. This is what I wanted to get to. Forget the numbers for a second. Just look at the actual algebra. Here's what this says, and take a look at wording. You can write this down yourself if it helps. Fn, also known as the scale reading, is equivalent to, or reads, your weight, which is over here, mg, plus mass times acceleration. So just like Morrow said, when you accelerate upward, you feel heavier. Well, the scale is reading you as not just your weight, but your weight plus ma. This is some positive quantity because a is positive here. If I were accelerating downward, a would be negative. And therefore, this would be a negative number, and it would take away from my weight, and therefore making me feel a little bit lighter when I accelerate downward. So the general thing we want to write here is this. If a is positive, we feel heavier. But in this case, if I look at the formula, if a were negative, we would feel lighter. And that comes right from the formula. Before we plug in any numbers, just use logic here. This is definitely a value that is positive. It's your mass. In this case, your mass is not given 10. Thank you. 10 kilograms here. And G is 9.8. So that's 98 right here. That's definitely 98. And then either we're adding a value or taking away a value. If we add a value, you get heavier. Acceleration is positive. But when acceleration is negative, you get lighter. Now, the answer to our question will end up being, in this problem, we have acceleration of 3 meters per second squared. So Fn is going to equal, in this case, 10 times 3 plus 10 times 9.8. So 30 plus 98, or 128. That's what the scale would read in this problem here. That is what the scale would read in this problem, 128. So how much heavier? About what? So look at this mathematically. This is 98, and this is 30. So about a third heavier than you normally weigh. Right? 30 out of 90 would be a third, and it's 30 out of 98, some number sense here. So it's as if you picked up a third of your weight and are carrying it on your shoulder. It'd be like weighing an extra 50 pounds. Literally, throw a 50-pound backpack on your shoulder, that's what you would feel like in this problem if you weigh around 150 or so. Good.
So this isn't directly about this problem, but so is the extra credit like you stand on the scale and like see what happens to your weight?
Exactly. The goal of the extra credit is to accelerate upward at some point and then accelerate downward at another point. So you might want to start at like floor, I'll give the example now, it's fine. So you might want to start at like floor 2, right? And just pick a floor higher up. And in the very beginning, when the elevator starts to move, that's when you're going to see the acceleration fluctuate. At some point in time, though, the elevator is going to reach a constant velocity. And you know that, right? When you're on an elevator, it's pretty smooth, the ride. And then when it stops, you feel that deceleration. So it's only the very beginning of the ride and the very end of the elevator ride that you're going to really want to focus on when it comes to recording and looking at the data flow. So you would start, and it doesn't have to be you again. It could be a sibling, it could be someone else, and you can just do the recording. So you start by recording what you see. Maybe you see 130 pounds. It's your brother, whomever. And then suddenly, you see it fluctuate from 130 to like 140, 150. Discuss what's happening there and prove it with your math here. George.
So if the acceleration was like enough to fall to the floor, because you can't like support your own weight.
Yeah, that's a great question. If acceleration upward were great enough, technically your whole body would drop to the floor because your legs would have to support that much weight. So if it accelerated like 12 Gs, well then your body weight is going to be 12 times what it actually is, which is like 1,600 pounds or something. So yeah, your legs probably wouldn't be able to support that and you would drop to the floor. Which is like rockets taking off into space. The astronauts are this way, that's how they're seated, and their whole body is pulled to the seat as they start moving upward. Yeah.
So this is kind of like a real world sort of thing. Like, you know the Tower of Terror in Japan. So when it goes down, you kind of come up out of the seat, and is that because of the acceleration downward, like that you were becoming lighter, or is it because that just the quick disappearance of the surface beneath you causes you to go up?
So the surface beneath you drops out so quickly, that's what causes you to elevate right away. Now you're strapped in, so you're not going to like literally fly off.
Yeah.
If the drop were at a rate that were less than 9.8, you would not actually lift off. Which means that the acceleration downward initially is probably slightly greater than 9.8.
Okay.
Because if it was at 9.8, your bottom would kind of still be on the surface of the chair, but kind of just off, you know what I mean, to be that in-between stage. But this means that it's greater than 9.8. And we're going to discuss that because this would be really, if you're going downward, this would be negative 9.8. So if this were negative 9.8 right here, and you were doing a free fall, you would get negative 98 plus positive 98, which would equal
0.
and that's weightlessness. So in that problem where the Tower of Terror drops, it probably drops to the number like negative 12, negative 13 as your acceleration. So you feel like, oh my gosh, I'm not going to catch this thing, and then your body gets caught by the straps. That's why you have a harness on. There's a lot of problems like this. A lot of the amusement park type problems with free falls and loop-the-loops involve this. Yeah.
How come the scale reads your weight in newtons?
Well, in this problem, we're doing everything in SI units, so I'm using newtons.
Okay, so
If you're at home and you're doing this extra credit, it's going to be right in pounds, LB. That's the force that you're using in the English system, LB. The mass in the English system is called like slugs or something. We just don't use the mass in the English system. Mass, we use kilograms pretty much. And if you ask someone that's from Europe what their weight is, they'll tell you in kilos, so they're really giving you their mass. They're not giving you their weight. So if somebody says, I weigh 200 kilos, they don't weigh 200 kilos, it's their mass actually. Their weight would be in newtons if they were using the proper system.
what does it do?
So for this extra credit, you can do it over the break, that's fine. Okay, so anytime before the test on the topic. So usually so last year I gave like 4 extra credits all year. And every time I give them, I try to make them do before the test so that you reinforce the idea before the test itself.
So you
And
just,
this test is not until after break.
do you just like record the numbers and write why it happened?
Yeah, so you're recording in the video, and you could either make a video out of it with your explanation, with your voice. You could have something written. You could do what I do and show the math behind what's happening in the problem. The better you do, the more you do, the more clear you are, the more you use math and logic and conceptual understanding, the closer you'll get to getting 3 points bonus versus 2 versus 1. Okay? So I kind of let everybody open-ended do the first one, and I give them a grade based on it. You're not going to get a negative score. It's never going to hurt you. So it can't hurt you to do this, you know? Yeah.
If you don't have an elevator, can you do it someone?
Sure, that's fine. As long as you both take a recording and I know, like, I want to hear your voice or at least, like, see your face for a moment so I know it's you doing it and not somebody else did it and then sent you their video. You understand what I'm saying? I want you to actually experience the feeling and explain it at the same, like, concept. I don't want it to be someone else's work and then you just use. So to follow up with the second part, like we just stated, what would make you feel weightless would be, go ahead, Jack. You had this earlier? Yeah. What would make you feel weightless in this problem?
You would need the acceleration to be negative 9.8, which is the opposite of gravity pretty much.
And therefore, the sum of these numbers,
They balance each other out.
they balance each other out. So if the acceleration of the elevator were negative 9.8, that's a free fall. That's what it is. And we've already talked about this idea. When objects are in free fall, you feel weightless. Has anybody skydived in the room? Jack, you have? What's the indoor, outdoor? Yeah, I want to do indoor. I'm actually indoor on my ears, right?
I went big skydiving.
Did you go on the fan? But you feel like you're floating, right? Your body, you feel like there's no weight.
You feel like you're being attacked. I know you feel like you're like
That's what
all of your faces are like.
yeah, you're vibrating.
He's like, oh, that's not supposed to happen.
All right, let's move on. So the answer to the second part was A equals negative 9.8, okay? That's the second part of the problem right there. Let's move on. So, let's talk about this idea of tension. We've already talked about it several times. We haven't really gone into it in the nitty-gritty. You saw it as a quick question there the other day. So tension is the concept that if you attach a cord, in this case they say a string, a rope, a wire, whatever one uses a phrase, but a cord to something, you can pull on it with tension. So let's take a look at this great example we have here today. So we've got the tension in this cable. I'm down, don't worry. We have the tension in this cable, and I'm purposely pulling at an angle, not like this because I'm nervous that it comes topple over. So by pulling at an angle, I'm also pulling in the vertical, not just the horizontal. So I'm doing here. So as I apply tension to this rope or this bracelet, which is very nice, that rope or bracelet applies its tension force to this carabiner, which then in turn applies a force to the bottom. So what we have here is an example of like a 3-part system. The rope, the mass connecting, and then the actual mass itself. So tension is simply used to transmit a force. It's to transmit a force. A rope, all a rope does, or like a pulley, it redirects it. So if I had something like this, where I'm loading, let's say this is a truck. And that's the back of the truck. There's an opening. Here's the front of the truck there. And let's say we've got a ramp from the truck here. And you have a very heavy thing, like say a piano or something. You're trying to move it. And you hook a pulley system up here and attach it and apply a force there. So let's say, again, you have like a little pulley, a little wheel here. You run a rope over it, attach it to the piano, so that 2 or 3 people can each get hold of the rope and pull on the rope to separate the amount of force or to distribute the amount of force upon each person pulling. So we might have 3 people standing in this truck all pulling on the rope. Well, 3 people pulling on the rope create 3 forces this way, or a giant force to the left. Well, that force then transmits to this object right here. Okay, that force on the rope pulls, so people pull on the rope literally, which then pulls on the mass itself. So tension is a redirection. It's a redirection of your force usually. Now, for the example I just gave with Caroline's water bottle here, that's not the circumstance, because I'm not actually redirecting the force. If I held onto her water bottle and pulled like this, versus doing this, either way, I'm having the same force actually, doing that or physically pulling it. It's when we change direction over a pulley or around some object that the tension in the wire physically redirects that force itself. But this is the best application of tension and where you're going to see it. So we'll start with that as an example, or as a definition, and now we'll look at an example of it. So the first example is pretty much what we were just doing there. So the first example is a person pulls on a 10 kilogram box by an attached cord along a smooth surface of a table. The magnitude of the force is 50 newtons, and it is exerted at 25 degrees, at a 25 degree angle northeast. Calculate the acceleration of the box and the magnitude of the upward force exerted by the table on the box. So we've got 2 things to do here with a general idea. So the general idea is we've got this mass. Our mass is given as 10 kilos to start. We're told that the force applied is 50 newtons. We're told that the angle it's applied at is 25 degrees northeast. And we want to figure out the acceleration. And then the last part says the upward force exerted by the table on the box. Upward force exerted by the table on the box. What force is that we're looking for in that circumstance? What do we think is the upward force? Again, exerted by the table. The table is the surface. What force is always exerted by the surface? It's only one force. Isabella?
Normal.
The normal force is right. So we are looking for the normal force in this problem here. It doesn't say it directly. This is where we need to break down the problem and recognize what it's asking. And whenever you hear a table or a surface applying an upward force, that's Fn that we're looking for. All right, so draw a free body diagram. Draw yourself a free body diagram of this. It should take only about 30 seconds. I'll give you a hint. There's only 3 forces acting on the body. 3 forces. Start with your dot, as always. By the way, in some of my notes, I use a box instead of a dot. Sometimes I do that if it's like you're moving an object that has some depth to it, or size to it, like a couch. There's a problem we're going to do later on. So a box or a dot are pretty interchangeable. So it could look like this. Okay, either way it could look like really to start. And on an AP exam, sometimes they'll put a little box there and you have to draw the forces acting from it. Sometimes it'll be a dot. It's interchangeable, it doesn't matter. So what forces, quickly, what forces, just name them. Name them, Caroline, give me one.
Gravity.
Gravity acts. Good, acts down, very good. Gravity always acts down. Julia. Normal acts up. And when we say up, we assume up in the y direction right now because we only have the x and y direction. And finally, the last force applied is the last force. FP. And how do we draw that tomorrow?
I think you do it like if it has a plus 25, I think it's northeast.
Yeah. So what's northeast? Give me directions. Which way? Down, left, up, right? What? Right and up. Very good. And the angle is between the horizontal. Okay. I might put P for pull. That's fine. Let's use P for pull. Now, why don't I need to worry about tension? Oh, there's a rope here. Usually I have to think about tension. Here's the thing again, though. The tension in this rope is transmitted by the force I'm applying. So whatever FP I pull on the rope, that is going to then in turn pull on the object. So right now, I don't have to worry about labeling this FT and solving for the tension in the rope and worrying about that. But when we have a multi-body system, which we're going to have soon, 2 masses hanging over a pulley, then we have to worry about tension in the rope and label FT, and we'll get to that point. But I want to point out to you guys that some problems will have a rope and there is tension involved. But I can just label this FP because the pull that I exert on the object is physically acting directly on it. So whether I call this FT or FP, it's the same thing as a problem. Later though, we're going to see where we want to call it FT for a specific reason. So if I look at this arrangement, what do I have to do with FP right away? What do I have to do with FP like we've done in the past? We did it in lessons 4.1 to 4.5 a couple times. We also did it with velocity, with V naught. We'd always do this with velocity when it was at an angle. What do I have to do still? I got to do something, right? George, what do you think?
Split it into the X and Y components.
Split it into components. I agree. So here's what I'm going to do. I'm going to redraw my free body diagram right below it. I'm going to still include FG and FN. And then what I'm going to do is this. I'm going to call this FPX. And I'm going to call this FPY. So I've redrawn my free body diagram there. Oops, let me make it a little bit better. Okay, I've redrawn my free body diagram in the bottom right. That's what we need to be visualizing right there. Anytime a force is at an angle, you gotta break it into its components. Components are probably the number one most important thing in physics that you learn because it applies to every topic in physics. So when we want to think about something at an angle, we have to automatically put it into its components or break it down into its components. The X is only labeled X because it's going left to right, and the Y is labeled Y because it's going up and down. Had this force been at an angle like this, I would still have FPX, but then FPY would be downward, right? The same thing goes for a force acting like this. It would then be FPY upward and FPX to the left, and the same for the southwest quadrant, okay? So keep that in mind. The direction of your vector indicates the direction of your components, just like it did with initial velocity.
If you have a force in the northeast direction and in the southeast direction, same force value, would they equal out and it just goes horizontal?
If the angle and the forces are identical with the vertical and the verticals balance, absolutely, Jack. Yes.
So it would just go.
Yep.
Okay.
You hear his question? Imagine the exact same force, FP, with the exact same value at the exact same angle, but below the horizontal now. The y component of this force would be down. The y component of this force would be up. Those components would balance, provided again that FP and theta were the exact same numbers. And then therefore, these two forces pulling like this would only cause the object to move in the x direction. You know what example you're thinking of? When they tow boats in a canal. A lot of the time when a boat goes through a canal, they'll hook up ropes to the side of it. The reason they do it is, God forbid the boat could sway left to right and actually hit the side of the canal. The boat itself could be damaged and the canal. So they'll hook on ropes and they'll actually pull a boat through with ropes with the exact same diagram with a force like this, okay? And this is the canal right here. And the boat will get pulled through with a rope in that direction and a rope in that direction. That's actually a very applicable example of what you're thinking of. You're going to see in your questions, one of them is exactly what he was talking about there. One of the homework, not homework, but one of the, whatever, long answers, yeah.
When do you use the first diagram versus the second diagram?
So what I like to do, and I personally always draw the second diagram as my diagram. I was showing you the first diagram because this is the first time we really looked at forces at an angle. We did it really quickly in 4.1 and 4.5, but I would always use the second diagram. Okay, I would always draw the second diagram. It doesn't matter though. Technically, both are correct. Now, on an AP exam, they may give you the first diagram as something in the problem given. And that's fine. You could then just redraw it as the second diagram. And they'll usually not be as nice, but if it were me and I were doing this on a test, I would definitely break it into components because it makes life a lot easier for me. And here's why it makes it easier. Now what I do is I recognize again, I can look at the sum of the forces in the y direction, and then I can also look at the sum of the forces in the x direction. Okay, I can look at both of those equations. It's never going to change. That's the nice part about this chapter. I keep saying it over and over. your sum equals ma, your sum of the forces, your governing equation is always the same. It's just about what direction we act in. What direction we act in. So, right off the bat, this is a person pulling on a box. Let's not forget the problem we're looking at here, right? A person pulling on a box. It's also you pulling on a sled. It's the same problem. It's also, you ever see those strongest man or strongest woman competitions on ESPN? They like pull a truck. Anybody ever seen this before? It's crazy. These guys, or women either, but usually for this event, it's these cute guys. They'll like put this like thing in their mouth, almost like a horse would pull on a carriage, and literally pull on a truck all the way at one step. Well, that's this problem, guys. You're laughing, but that's exactly this problem. Look, there's a cable attached to a person pulling to the right. Here's the weight of the truck. Here's the ground pushing up. What I want you to start recognizing is how to model problems. I keep saying it. Those that are getting 90 plus on their tests are really good at modeling problems, and I noticed that because you understand right off the bat. So if you're struggling a little bit, start writing this down in your notes, right? Don't laugh about it. Start writing in your notes. This could be a person pulling on a sled. This could be, again, that strongest man competition of somebody pulling on a truck. This could be a horse pulling on a carriage because it's usually at an angle. It's not directly horizontal. So this exact example here could be applicable to thousands of situations. And yet the free body diagram would look the same for all of those situations. This free body diagram wouldn't change for any of those ones I just named there. Now, if we incorporate friction, which we're going to do in section 4.8, we would have to have a force acting against motion. And we'll see that when we incorporate friction a little bit. But we're still looking at a simple scenario without friction. So, in the y direction, here's what we have to think about. If we were pulling on a box or a sled, even if we pull on it really hard, it's most likely not going to levitate off the ground. I would have to pull on this bottle. Is this going to break if I hold on this?
Probably not.
I would have to pull on this bottle with enough force to lift it off, right? So if I pulled on it with a light force, it would just be literally dragging it. It's not lifting vertically. This is great to put it in today. It's a perfect time. So yeah, it's not lifting vertically at all. It's only moving horizontally. So if it's not lifting vertically, what can we say about MAY? What's MAY going to be if it's not physically moving vertically at all?
Zero.
It's got to be zero. Okay, for these problems, remember, we're not going to have vertical acceleration for a lot of them if an object is only moving across a floor or a surface. So this will become the following. The sum of the forces in the y direction. What forces are acting in the y direction? We've got a couple here. Give me one, go ahead.
FPY.
I agree. FPY is a positive force in the y direction. What else is another positive force?
Normal force.
Normal force. And finally, what's the only negative force?
Gravity.
Gravity is the only negative force, and that equals 0. So I'm glad that you guys are picking up on this by now. It's literally a game of, hey, let's just draw the free body diagram, and then you have to just list the forces. That's it. Every single time. These are both up, they're both positive. This is down, it is negative. And that's it each time. The question is, well, what's this, right? We're going to get to that. What is this value? Think about how you would break up vectors with velocity. If you want the y value, you have to use a trig function. If you want the x value, you have to use a trig function. So think about what trig function that would be. Now, in the x direction, there is acceleration. There must be acceleration because the problem says calculate the acceleration. But also because there is no negative force in the x direction. Look at your free body diagram right now. Without friction, which we assume there's none in this problem for now, we're going to get to friction. Without friction, the only applied force is pulling this object this way. That's it. Oh, sorry, this way in this problem. So if there's nothing pushing back, it's got to accelerate this way. Because what's the definition of a force? A force is a thing that causes acceleration. Think back to 4.1 to 4.5. Forces cause acceleration. That's what Newton told us in his laws. So as a result, if there's an unbalanced force in the x direction, there must be an acceleration resulting in the x direction. So we know already that this ax will be a value, so that's not going to drop off. That is going to be a value, so that carries down. And then the only force acting here is Fpx. And that's acting in the positive direction. So I write Fpx. Again, had friction been there, we'd have minus friction, right here, minus friction. If friction were acting against motion, okay, which it will soon. At this point, it is a plug and chug, right? And I know it sounds like it's easy, but I know it sounds like I'm making it easy when it can be difficult, but it's not that bad. This becomes FP sine theta plus Fn minus mg. So what I'm doing right now is I'm replacing any formulas that I know. I know that the y direction of a force is always that force times the sine of theta. So again, I drop the y as a subscript and I replace that with multiplying by sine theta because that's what the y component is. I replace Fg with mg, just like we did the other day and we've done several times over now. And then in the x direction, we've got Fp cosine theta because that's what we're looking for. So again, these are uncoupled equations. When I use the phrase coupled equations, it usually means you need to use them together to solve, like a system. Why is this uncoupled? Why is this not a system to be solved, Christina?
You can find the acceleration in the x direction on its own.
And then,
And,
what's the other unknown?
the natural force.
Yeah, you can find the normal force in the y direction on its own. So these are separate equations completely. There's going to come a time, just like with projectile motion, where we have to solve for the x as an equation and move it into the y direction. Remember, time was our linking variable, as was VO and theta. Here, we're going to see later, we're going to have a linking variable, but that usually only occurs when we have to start worrying about friction. Friction is involved. So for now, solve for AX over here, and solve for Fn over here. Okay, so we've got AX is equal to FP cosine theta divided by M. And over here, let's solve for Fn. I'm going to add mg over, and I subtract FP sine theta. So those are my two answers for this problem. And yes, I can plug in numbers and get a value, but again, I don't care about the value right now. In the real sense of a problem, if you were an engineer designing an apparatus, you would calculate that value because it matters a lot. But right now, for the logic of physics, what matters is being able to get to this answer. Okay, now it's just plugging in and doing arithmetic, which you should all be able to do. FP is 50 times the cosine of 25, all divided by the mass, which was given as, I ran out of room, what was the mass given as? 10? Well, what do you get as, you have a number for me already? Yeah.
I got 4.5
For the acceleration?
Yeah.
That sounds good. And look like, get a nod from anybody, verification, yeah? Okay, George agrees, I agree, George, thank you. And then finally, the normal force is the other thing to calculate here. What do we get for the normal force in this problem? What do we end up getting? And again, it's just plugging in now, right? I'll point to it. This is 10 times 9.8 minus 50 times the sine of 25 is equal to what quantity? Awesome, 76.9 newtons, I agree. Okay, please check on your calculator. A couple of you are doing it, you don't have to, it doesn't have to be the same person every time. You should all be checking on your calculator. When you can't use your calculator on a test, I'm going to say something like, you should have practiced when we were in class, right? A couple of you last test asked me questions on the calculator, and I said, sorry, I can't help you with that. You need to see me before the test if you want help on a calculator, right? So I recommend that you practice during class, because then if you can't get it right during class, and these numbers aren't the same as what you got, then it triggers, ooh, I need to ask Mr. Howell how to go through this process in the calculator. So then on the test, it's ready. All right. Here's something we noticed. Let's make some points. First, the normal force. The normal force is normally equal to the weight. But since we're pulling up on this object, we're helping out the normal force a little bit. We're alleviating some of the force that the table has to push up with, which is why we're subtracting some other quantity to make the normal force a little bit lower than it would be, which would just be for this value. What would this value be? Just 98, right? This is 10 times 9.8. This would be 98 minus off some number, which is what making the normal force a little bit less, because we're lifting up on the object slightly, okay? And then the acceleration, there's nothing about it really here, but the more force you have, the more the acceleration would be. The lower the angle, the more the acceleration would be, because we know that the x direction is greater when the angle is lower, right? Think back to velocity. If I kick something at 45 degrees, it's evenly split between the y and the x. If I kick it lower than 45, it's more in the x. If I kick it above 45, it's more in the y direction. So since this angle is 25, the acceleration is greater in the x in a sense. So if I got this lower and made this 15 or 10 or 5, this value would go up. It would help the acceleration in the x direction if it were a lower angle. Or think about it this way. Look, acceleration is indirectly related to mass. And that's logical. You did that in the lab. When you were pushing on the refrigerator and the file cabinet, what were the other objects? It was like a sleepy dog, I think, or something like that. Do you remember the simulation I had you guys do? You haven't tried reading yet? Piano, yeah. So as the mass changed, the acceleration also changed. So the heavier or more massive an object is, the less the acceleration. These are indirectly related. So we want to use our answers to help us understand the logic behind the problem. The logic. Let's go back to Tom Cruise. He's back again. So, has anybody ever done this? Tightrope walking?
I've done like
Yeah,
like
the low one?
not the tightrope thing, but like the slackline.
Slackline, yeah, where it's like a, it looks like almost a it's actually a lot of fun. If you haven't tried this, if you haven't tried this, it's called slacklining. Is a different version of it, and it uses like, you know those like a canvas strap? Imagine a strap the entire way. So it's not really thin. It's like it looks like a piece of tape this long, but it has a lot of tension in it.
And it's between two trees. It's a lot of fun.
Yeah, between two trees. Right? Have you watched Modern Family? Anybody see Modern Family?
Yeah.
Phil Dunphy? You know Phil?
Yeah.
Phil's the best. He's so funny. Do you remember when Phil slacklines? He does it earlier in the season. He does it like season 3 or 4. It's good. Anyway, so Tom Cruise is walking across a tightrope. You know, imagine he's like Batman or something, you know. He shot this thing across, it latches onto their building, and then he has to walk across it in his jeans for some reason. I don't know. Gotta throw his head on there. So he walks across this tightrope from the top of a building to another. He's escaping his nemesis. As he walks across the rope, it sags in the middle slightly, okay, when he reaches the midpoint. The key to this problem, by the way, is the symmetry here. He reaches the midpoint, same angle, it's going to help us a lot. The angle shown in the diagram is 5 degrees, while his mass is 70 kilograms. If the maximum allowable tension in the rope is 3,700 newtons, will it snap? Will it snap? So again, the maximum allowable tension. So what does that mean? Give me a little synopsis of what we're going to be figuring out. It's based on what they're giving us. If the maximum allowable tension is 3,700, what are we trying to figure out?
We're trying to figure out like exactly how much mass the rope contains.
Close. Close. You're on the right idea.
Are you trying to figure out whether FG will be greater than 3,700 newtons?
No, good idea. You both have the right idea, but you said mass, though, and then you started talking about FG.
Are you trying to figure out if the normal force that's being exerted is greater than 3,700?
Not the normal force. I'm glad I asked this. It's open-ended. Yeah?
Could the force that Tom Cruise is applying on the rope will not exceed 37?
No. Good question, though. I see. It's so intriguing because you want to say if his weight down is more than 3,700, it'll snap, right? You would think that. The angle causes the tension in the rope not to be the exact thing as his weight. So it's not going to be like, we're just going to figure out his weight, and if this is greater, oh, it's going to snap. It's not going to be that, actually. But what do we know? We know the maximum allowable, what's the word? So what do we have to find? We have to find the tension force. This is the first time we're going to label a diagram with tension. So let's start. Let's start by drawing a free body diagram. We're going to draw a free body diagram of the location right here. See where I'm pointing? We're going to draw a free body diagram right there of Tom Cruise acting on that rope. So let's see what happens here. We've got Tom Cruise. We've got his weight acting down. How do I draw the supporting forces? Like, what's keeping him up? Tension. How do I draw it? Yeah, good, Jack. I draw it at some angle from the body itself, and it's going to be outward in this case. So the tension in the cord is literally the cord itself at a 5-degree angle. I like to call it FT for tension. The book here is calling it TR. Maybe relabel this as FTR, like the force of tension in the right rope and the force of tension in the left rope.
Mr. Howell, why
Yeah.
is it up? Oh, right. Sorry. I forgot.
Because he's technically pulling down on it, so the rope has to pull up to balance him.
Oh, I see it.
And that should be symmetric. That does not look symmetric, sorry. That other vector should be symmetric. That's a little bit better. I'm trying. This is FTL, and that's also an angle of theta. So my free body diagram is actually shown on the right here, and what happens is, if Tom Cruise weighed more than he does, what would happen to the line? It would sag further. So what would happen to the angle? It would be a greater angle. The heavier Tom Cruise is, the bigger this angle is going to be. Okay, it's going to sag more and more. Now here's the thing though. The assumption we have to make in this problem is that Tom Cruise is a fixed mass, which he does. And the angle isn't more than what we're seeing. So we need to figure out, what is the tension either side of the rope? And if that tension is more than 3,700, it's snapping. If it's less than 3,700, he's going to survive. It's not going to break. Okay? A lot of like imminent death problems. Yeah, go ahead.
Why is there no?
It's a great question. You hear the question? Why is there no normal force? A rope is not a surface. That's the reason, or the simple answer, Laura. A rope is not a surface technically, because a rope has tension in it. It is not supported by a ground beneath it. Surfaces are supported by the earth. So if I were to stand on this table, you might think of this problem the same way. The table kind of bends in the middle, right? If you think about it, I can take a piece of plywood, put a piece of plywood between here and here. Stand in the middle of the plywood. The plywood is going to bend, isn't it? The plywood is technically like a rope on each end, bending. So in a problem that doesn't have a direct surface below it, like a rope, we're not calling it normal force. Could we technically? Sure. What we could do is this. We could break this into its components, call this FTRX, FTRY, call this FTLX, FTLY, and then the FTRY and the FTLY going up together could be replaced by FN if you want to, and call it normal force. But when you don't have a surface, don't include normal force. Okay, good question there. George?
But even when we're doing a problem that's like someone's on a box or something, isn't the box gonna like depress slightly as well? So
It will. In this course, we assume objects are what are called rigid. So besides a rope that has slack in it, for actual physical objects, tables, floors, the assumption is that they're rigid. Yeah, but in reality, they do bend slightly. Even the strongest of materials have some slight fluctuation to their shape when you apply force to it. So let's take a look and think about this logically. In the x direction, I've only got two forces. Two forces in the x direction. One pulling to the right and one pulling to the left. And that's the tension component. Remember, this tension is at an angle. So it's got an x component and it's got a y component. This tension is at an angle. It's got an x component, it's got a y component. So we have two x components in this problem. One is pulling to the left and one is pulling to the right. So in the x direction, we've got the sum of the forces equals ma in the x direction. And then we've got the sum of the forces in the y direction equals ma in the y direction. Now, Tom Cruise is right now at this point right here. He's trying to get across this. The object, we assume at this moment, based on where he is, it's an instantaneous moment in time where he's like, oh, I'm about to fall. So without giving anything about acceleration. So although we might think, oh, he probably is accelerating, the assumption has to be that he's walking either at a constant velocity across the road, or that for a moment in the middle he kind of lost his balance, and this is what we're seeing. We're seeing a freeze frame of this right now. Because we're not given anything about acceleration in the x direction. We're not asked to figure it out, so we can't have any sort of acceleration value in the x direction. So when we look at this problem, we say to ourselves, okay, well, this is interesting. Let's see. We've got those two pulling in opposite directions. So it looks like we've got negative FTL cosine theta, and then a positive FTR cosine theta. And that's going to equal 0. Again, because the assumption here is that he's not accelerating. He's moving at a constant velocity as he walks, or he's stopped in the moment stopped in the middle for a moment. Now, just take a look at this and think about it for a second. The angles are the same, aren't they? So what happens as a result? The angles are the same. What are you thinking?
The angles are the same, like sine 45 and cosine 45. They cancel each other out.
For sine and cosine 45, they're not 45 here, right? The angle's 5 degrees.
Equal,
I'm asking about this equation. Somebody else is asking about this equation specifically. If the angles are the same, what can we do? Come on, math people. There's somebody that is supposed to be geniuses at math. Let's go, let's go, let's go. Then go. Yes. Factor cosine theta right out in front. Why does that help? Why does that help? Come on. Why does factoring out a cosine theta help you? Think about it, George.
It just simplifies it.
Yeah, it drops off actually. It simplifies to be nothing because look, isn't this a 0 here? So by taking cosine theta out in front, you could then divide both sides by cosine theta. So technically, let's just divide the whole equation by cosine theta at this point. Divide this by cosine theta in all 3 spots. So I'm doing what Vince said, which is technically factoring out, but I'm trying to do it all in one step. Divide by cosine theta in all 3 spots in this equation. This becomes negative FTL plus FTR equals 0. That's the result. That result is really important. Why is this result so important? What does this signify? Let's go to the next step if it helps you. Yeah, Caroline.
The FTL and FTR are the same value.
Yes, they're the same values. That's really important here. If I move FTL over, it looks like this. That's the result we get in the x direction. And that's the result we get in the x direction. So because the angle happened to be 5 degrees in both spots, or for both chords, the angle actually drops off. We divide by cosine theta in all 3 spots. We could have plugged it in, right? We definitely can. We can plug in at cosine of 5 degrees here, cosine of 5 degrees here. We're going to get some decimal in both spots, which we can then divide through by that decimal. It's the same exact thing. What I'm trying to point out is this. With an equation, if every single term has that factor in it, or if one of the terms is 0 also, it can cancel out from all of them. So if I had mass here, and maybe even mass here, the masses would cancel in all 3 spots. Or just an m here and an m here and a 0 here, we could divide by mass, divide by mass, divide by mass. 0 divided by anything is still 0. That's the key to this problem. Okay, you're really using the 0 product property, back from algebra 1 and algebra 2. Okay, but it's inherently using division, because remember multiplication and division are really the same thing. So this is the conclusion that helps. Why does this help us? Anybody have an idea? Why do you think this is going to help us? It's just telling us that they're the same right now. That's all it's saying right now. What do you think, Christina?
Tom Cruise is distributing equal force in both directions.
Okay, good. Very good. Mathematically, how's it going to help us now? Mathematically.
I'll use it to substitute
Probably use it to substitute in the
in the
y
y direction.
direction. Okay, there's a good chance that, because we didn't get a number, right? There's no number yet. We still don't know what the tension is. We just know that the tension in both directions is the same. That's all we know right now. The tension in both directions, FTL and FTR, is the same value. That's the key here. Because in the y direction, let's take a look at what we've got now. In the y direction, the force that's pulling up, FTL sine theta, that is this component right here of this force. That's that component right there of that force. Plus, let me go back to black. FTR sine theta. That's this component, blue, of this force over here. So the red and the blue that are stacked here on my free body diagram are replacing FTL in the y direction and FTR in the y direction. Because technically speaking again, right, FTR is blue. That pulls right and up. FTL is red. That pulls left and up. So if I look back at my free body diagram, I've replaced FTL and FTR with the red and blue vectors. Notice, the left and right vector, they balance each other. That's this statement right here. This statement right here that we just came up with in the x is this. It's saying, hey, these are the only 2 forces, so they must be equal. Okay? The horizontal projections or components are balancing each other, which is validated by this statement right here. But vertically now, we've got both of these forces acting up. A tension component of the rope. And what's acting down is simply Tom Cruise's weight. Minus Fg. And we're not having Tom Cruise jumping up and down on this cord, because he's already having trouble staying on the cord. So he's not going to have any vertical acceleration. So that equals 0. So again, the question was, why is the x direction important to get a result from? Because if I started in the y direction, how many unknowns do I have right now? How many unknowns? Look at the y direction. Think about what is given in the problem. and answer the question of how many unknowns would I have in this problem? Which of these are unknowns, which are known? You would have two unknowns. FTL and FTR are both unknowns. Sine theta is known because it's 5 degrees. Sine theta is known because it's 5 degrees. FG is just mass times gravity. That's Tom Cruise. He's 70 kilograms, so 70 times 9.8 is this number. So what we don't know right now is FTL and FTR. But because they're the same, we can say instead, let's just call them both FT. All right? Remember how earlier I said to you, if I have two different objects, I'm going to call them M1 and M2, or MA and MB. But if the objects have the exact same mass, I'll probably just call them both what? Mass.
Yes.
I would just call them both M. Not M1, not M2, if they were the same mass. So since the tension on the right is equal to the tension on the left, let's replace both of those variables with just simply FT, because they're identical. And what that does is that gives us only one unknown now. And I'm going to replace FG with MG, as we always should. Tension is the only thing unknown in this problem, and it appears twice. That's okay. I have FT sine theta plus FT sine theta, so that's just 2 FT sine theta here. Okay, don't let all the variables be the thing confusing right now. These are like terms. This is like saying xy plus xy. You would have how many xy's? You would have 2 xy's. 2 xy. And then minus mg just carries down. And at this point, our goal is to just solve for ft. I'm going to move mg over. And then I'm going to divide by 2 sine theta. And there's my actual answer for the problem. Now, here it does matter that I get a number. Why does it matter that I get a number for this problem? Maura, why do you think it matters?
Because if you see if it's greater than 3700.
Yeah, the goal is to figure out, is this number more than 3,700? Okay, remember, where are we plugging this concept in? We're plugging this concept in here, which is what gives us ft in both those spots. So let's plug in for mg, 70 times 9.8. Let's divide that by the quantity 2 sine 5 degrees. Divided by the quantity 2 sine 5 degrees. Again, this is the kind of problem that if you don't use your calculator well, you could absolutely make an easy mistake. And I can tell you, I could probably actually guarantee you exactly what mistake you would make here. And some of you probably noticed it also. You've got to figure out what would the mistake be that students might make on a calculator if they're not really careful.
You don't put that 2 sine theta first.
This needs to be in parentheses. If you type in 10 times 9.8 divided by 2 times sine 5, it's going to divide by 2, get an answer, and then multiply that answer by sine 5. Remember, this is a quantity, and the calculator doesn't know that it needs to divide by the whole quantity, so you have to tell it. So put parentheses around your denominator. Does the numerator need parentheses? It does not. But if the numerator had a plus sign in it, then it does need parentheses. You got to know how to use a calculator. A tool is worthless if you can't use it well. George.
So the only steps you really need for this problem are like the last two there, because once you know that.
For computation, you mean? To get the answer, or what do you
Like
mean?
if you just see this type of problem on a test, can you just?
Yeah, if the problem like this has symmetry, and you have like 2 chords pulling up on an object, you can right off the bat say that the x components are the same, which makes the tension in both cables the same, and you can kind of jump ahead to this step right here. I actually gave a multiple choice problem on the AP physics test, like 2 weeks ago, and it was a cord, 2 chords being attached to a mass, moving it upward, lifting it upward. And this was the generic solution that you could have jumped to. Yep, very good, George. And you're going to see that a lot of these problems have that idea, where you can have a model to the problem and have a generic solution. Okay? Had this been accelerating upward, like it was being lifted, this would just no longer be 0. You would have MA over here. But the rest of the problem would carry down, and the MA would have to be accounted for. But Tom Cruise is not moving vertically upward, so we don't have that. What do we get as a number? What's the value? What's the value?
3,945.48.
Agree? Disagree? So what happens? He's done, right? He's done. The maximum tension is 3,700. That rope snapped. Luckily, though, of course, he's got some sort of a parachute. He pulls it out and he saves. All right. Happy day. Example 8. Example 8. There are a lot of examples you notice in this section. Okay, a lot of examples. One paint bucket hangs from a massive cord, and a second paint bucket is attached to the first one. Each of these have a mass of 4 kilograms, the paint buckets, and they are at rest. What is the tension in each cord when they're at rest? Second follow-up. If the 2 buckets are now pulled upward with an acceleration of 1.25 meters per second squared by the upper cord, what is the new tension in each cord? So, we're going to do this problem once, and then we're going to redo it, where acceleration is no longer 0. In the first problem, they're at rest, so acceleration is 0. We're then going to redo the exact same problem, and the acceleration is now going to be 1.25. You follow me right now? It's literally the same problem twice. So my recommendation is you do what we've been doing and solve algebraically the first time through. And then you can just simply change A to be 1.25 the second time through. You don't want to do this problem actually twice on a test. So let's show that here. So let's draw a free body diagram of the objects. Here's bucket 1. There's tension pulling up. What else is acting on object 1 here? Seb. Gravity for sure. And what else, Seb?
And the mass of the second object.
Which is transmitted through the rope, right? So what should we call that actually? Yeah, another tension. Should we call them the same? Do you think they're going to be the same value?
No.
The upper rope supports both masses, right? The lower rope only supports the bottom mass. So we should subscript our tensions. FT1 and FT2. So that's the free body diagram of the upper mass. And let me go through it one time a little bit slower again. You are pulling on this object with some tension in the cord. This object is attached to another one through a cord. So as a result, the lower object here is pulling on this cord. This cord is in turn pulling on the upper object, which is what FT2 is. The weight of the upper object is just Fg, and the tension in the upper cord is pulling up on it. So that's the first object. How about the second object here? How about the second object now? I'll use blue for the second object. Bless you. Caroline.
It has the force of gravity and the upward force of tension.
So force of gravity, I agree, and it's the second object, but they're the same, it turns out, so I'm going to leave Fg the same. They're both 4 kilograms, so I'm just going to call them both Fg instead of Fg1 and Fg2 because they're identical. And what am I going to label that upward force, Caroline?
The upward force?
You said upward force pulling on it, but what am I going to label it as? What's pulling directly on the bucket, Caroline?
The rope.
Which is called? What kind of a force?
That's a D.
Yeah.
Yeah. So FT3 maybe?
Interesting, right? It's actually FT2. Let's talk about that for a second. Okay, we haven't done this yet. That's all right. So, as many ropes as there will be that many tension forces. Write this down, please. For as many ropes as you have in the diagram, there will be that many forces of tension. So there are only 2 tension forces here. Because there's an upper rope, which has FT1, and the lower rope, which is FT2. Again, for as many ropes as there are that many forces of tension. And think about this. Newton's third law. Newton's third law. For every action, there's an equal and opposite reaction, which is why FT2 appears in both diagrams. The amount of force that's applied to the bottom mass is a result of you pulling up on the upper mass. Well, you're physically pulling on the bottom mass with this much force. It's pulling back down with this much force. This is Newton's third law right here. Again, you pull up, which literally pulls up on the bottom mass. The bottom mass says, no, I want to stay where I am. I'm going to pull back down. And it pulls back down. That's this FT2 right here. So this problem is a perfect example of a multi-mass system with multiple tensions involved. It sounds overwhelming at first, but once we get the free body diagrams down, it's a piece of cake. Okay? Piece of cake. Let's discuss why it's a piece of cake now. Well, we're told that they're at rest in the first problem. That makes it even easier. They're at rest. So if they're at rest, A is 0 for the whole problem. Here's why it's also a piece of cake. There is no X forces applied at all in this problem. So I only have to look at the sum of the forces in the Y direction. Now, for two objects, sure. So I'm going to have two equations. But they're both sum of the forces in the Y direction. We've got object 1 and object 2. So let's go ahead and write it down. Here's object 1 and here's object 2. Object 1, I've got the sum of the forces in the Y direction equals MAY, which is 0 because it's at rest. Sum of the forces in the Y direction equals MAY. Again, 0 because it's at rest. I don't have to call it M1 and M2. Why not? Why not? The masses of the buckets are both 4 kilograms. They're identical. So there's no reason to designate M1 and M2 in this problem. So on the first object, I've got tension pulling up. We've got the weight pulling down. We've got the other tension pulling down. And that's going to equal 0. And that's the first object. Notice on the first diagram, we had 3 forces labeled. And in my equation, I have 3 forces listed. The second object, we've got tension pulling up from the second cable, and we've got the weight pulling down. And that's it for the second object. I'm using blue so you know I'm coming from the blue free body diagram only, okay? The second free body diagram gives me the second equation. As a result, I can solve very easily for this problem. Now, before I solve, I want you all to look up and notice something. Ready? I'm trying to get FT2, and I'm trying to get FT1. I'm missing both here, aren't I? So do I want to start here? Probably not, because I don't have either. But here I can get FT2, can I? By just moving this over and we know this value, then plug that in here, give me FT1. Second thing to notice, that's number one. Second thing, if this object is now accelerating upward, which it will soon, right? It's going to accelerate upward very soon. This now becomes m times 1.25. This now becomes m times 1.25. Because if I pull up on the upper object with an acceleration of 1.25, if I pull up on the upper object, okay, imagine the upper object, and here's the rope connecting to a lower object. If I pull up on the upper object, the rope pulls the lower object up with the exact same acceleration. So the second part of this problem here is going to involve MA and MA in both parts. And that's the only thing that's going to change for the second part of the problem. So if you want to, you can leave MA here and just set it equal to 0 in the last step. And then for the next part, just set it equal to 1.25 if you want to. Or we'll go back and just plug it in. So let's get FT2 here. FT2 will equal FG if we move it over. And FG is really MG. So it's 4 times 9.8. Right? 4 times 9.8, 39.2. That's the tension in the lower cable. And think about that logically. What does the lower cable support? What does the lower cable support? Physically, what does it support? The lower cable. What are we thinking? George, what are we thinking? The lower bucket only. And look, all we took into account was the weight of the lower bucket. This is the weight, Fg, of the lower bucket. The lower rope supports the lower bucket. Next, look over here. We're going to have FT1. And if we solve for FT1, we're going to move both of these over, aren't we? So let's do that. Let's algebraically move them both over. We've got FT1 equals Fg plus Ft2. But let's use logic right now. Ft2 is equal to the lower bucket's weight, correct? Ft2 is the lower bucket's weight, which means this is the weight of the lower bucket, and this is the weight of the upper bucket. The upper bucket and the lower bucket together are supported by the first rope. The logic makes sense. Look at the diagram. The first rope up top has one bucket and a second bucket pulling on the upper rope. So this is the weight of the upper bucket, and inherently, this becomes the weight of the lower bucket, really. And that's coming from here. So I can take that 39.2. I know this is going to go in right there. So the upper rope supports the weight of the upper bucket plus the weight of the lower bucket. As a result, the entire answer is 78.4 newtons. So that's the tension in the upper cable. Double the tension in the lower cable. So here's what you need to do. You need to go back at this point, take a look where I'm putting asterisks, and instead call this MA. And instead call this MA. Go back to that line, call those both MA. And plug in for A as 1.25 and M as 4, and resolve these problems. You're going to see changes drastically when you're suddenly being accelerated upward. Okay? Besides starting your homework, you were to finish this problem off. And what you'll notice is this. The answers for this come out to be pretty reasonable. And the answers actually are logical and make sense. Let me put the numbers down first so you can see them. So this was without any acceleration on the upper bucket. And then suddenly, the upper bucket is accelerating at they're both accelerating at 1.25 meters per second squared. It turned out that FT1 becomes 88.4 newtons, and FT2 becomes 44.2 newtons. And let's talk about this real quick, because the answer is what I want to go over, not the work to get to it. The work to get to it you should have done already. The lower bucket is the only thing acting on this lower rope. It's pulling down on it. So it turns out that this goes up by 5 newtons. As soon as we apply an acceleration of 1.25, and the mass is 4 times 1.25 is 5. That's where this extra 5 newtons is coming into play. Again, initially the lower bucket wasn't moving, but now we have acceleration upward of 1.25 on a mass that's 4 kilograms. That MA gives you another 5. Here though, notice what it went up by. It went up by 10. This one went up by 5, but this one up by 10. Why the difference? Why the difference? That's the real question we want to answer. Why does this go up by 10 in tension if the other one only went up by 5? What do you think?
Because you do it plus 5 to both of the values.
Yeah, very good. It's both buckets now. The upper tension supports not only the first bucket, but also the second. So the acceleration felt by both buckets is a 5 and a 5, like Jack is saying, because really, they're both now moving up at 1.25, and that upper chord, which is FT1 carries both buckets. So its tension goes up not by 5, but by 10 instead. Because, again, the acceleration is 1.25, and the mass of both of these objects is 4 kilograms. And if I multiply those two, you get 5 newtons. That's the differential here, because it was only one bucket being supported by the lower rope. But the upper rope supports 2 buckets. So the MA for the upper rope is not just 5, but 2 of those, which is why it goes up by 10. Okay, I wanted you to finish this so we can move on, obviously. Okay, so let's go on to the next question. If you didn't do this, you got to go back and do it. Okay, that was part of your homework. I'm not going to go through the steps that give us FT1 and FT2 for the new. So this one you should recognize. Where should you recognize this from? The quiz. It's the same free body diagram we're going to use. So if you struggled on the free body diagram, we're going to go over it now, obviously, with this problem. But start thinking about it based on what you now know. So first, one object is at rest or is on a surface connected to a rope, connected to another object that's hanging off of a pulley. MB is not in contact with the wall. If it were, it might have friction. But this problem as a whole doesn't have friction. Okay, we're going to be looking at a massless object and a massless pulley, and friction is not even mentioned. So we're going to see that this is not a friction problem. We're going to look at friction in our next section here. So the two masses are connected. The mass of the first object is 20 kilograms. That's up here. All right, that's the 20 kilograms. And the second object is 4 kilograms. Determine the acceleration of each mass and the tension in the cord. So, like all problems in this chapter, we start with a free body diagram. Okay? You can start with a sketch if we wanted, but we have a sketch already. If a sketch wasn't given, then maybe you want to draw a sketch, but it's given already. So let's start with object A and object B. Now, a lot of you know what the answer is because you had it on your quiz and got it right, or you see the correction on your quiz. But to mentally see this, I'm seeing object B that's pulling down with its weight. So for object B right away, I know that there's going to be some sort of a weight for object B. And the only thing acting on object B is that rope. And ropes can only do what? Ropes can only
move in one direction?
Not necessarily.
Transfer of force.
Okay, but more than that. More than that. We talked about it quickly last class. I said ropes can't push. They can only pull. So this rope must be pulling which way in this problem? Which way? Okay, so let's go over this. Only up. And let's talk about why. If the rope is above the object, to move it down, it would be pushing. Think about that. For the rope to somehow cause object B to move down, it would be pushing it downward. And a rope can't push, it can only pull. So whenever we draw our tension force for a rope, it always acts away from the object that the rope is attached to. Write that down if it's not clear or if you don't see that. Again, tension, Ft, only acts away from the object that the rope is connected to. And it acts in the direction that the rope is shown in the diagram. So the rope is above the mass, so the vector points above the mass. The vector points above the mass. But what about for mass A? For mass A, what is our tension force going to look like for mass A? Justin, what do you think? Only to the right. Because again, tension or a rope can only pull. So if the rope is on the right side, it must be pulling it to the right. It cannot push the object to the left. Again, the rope cannot push it left. Now, besides that, we've also got gravity from the first object. Is that it? What's the other thing, Seb? Acting?
On the table.
From the table. Right? From the table. An object or a normal force acting on the object from the table. Why is Fn so important in my diagram? Like if I left Fn out, right? Because in this problem it's going to turn out Fn doesn't even matter calculation-wise. We're not going to use it. But why is Fn conceptually really important?
Wouldn't the object go down if there was no Fn because of the force of gravity?
Exactly. Gravity would be unbalanced if it were not given with an Fn acting up. So then this object, object A, would therefore be accelerating downward. But it's not. It's being it's being placed on a table or on a cliff or a ledge or whatever you want to call this. The object itself with an unbalanced force, if Fn were not here, would show downward acceleration. It would have to be physically moving. But we know that it's balanced by the table, so Fn opposes Fga. Again, for this problem, it turns out that we're not going to need Fn actually. It doesn't actually matter at all. If friction were involved, like it's going to be in the next section, then Fn matters a lot. Fn is used for friction a lot. All right, now that we've got our two free body diagrams, we need to write our equations of motion. Equations of motion. So, what do we got here? Somebody give me either one they want to choose to start with. It doesn't matter which way. What are we thinking? Yeah, go ahead.
We start with A. So, like, the one I used on my homework was tension equals mass times acceleration plus gravity.
So, gravity's acting in the x direction on object A?
No.
So we can't include gravity if you're talking about tension, because tension acts in the x direction, right? So you're on the right track, Caroline.
Okay.
You're on the right track. You're on the right track. What else? For the x direction. Only the x direction we're looking at right now. Only the x direction. We can look at the y direction. That'll help.
For the x direction, wouldn't it just be tension equals mass times acceleration?
Tension is the only force acting in the x direction. So let's start by also making a statement. These objects will move. They will 100% certainly move. There is no friction in this problem, right? The only thing that would oppose the motion would be friction. Think about it logically for a second. Put anything on the table. Attach your mass off the edge. If there weren't friction, this object has to move. It's impossible for it not to. Okay? Because again, this is pulling down, which causes tension in the rope, which then pulls on the object. Is there anything pushing back here? No. There's no force of friction acting to the left. So Ft being unbalanced means that the object on the surface will absolutely move to the right. And we know that for a fact right now, because there's no force balancing Ft for object A. For object A. More?
So would it be the sum of forces for AX equals FT?
Yeah, so we'll start with that. So I can start with sum of the forces in the x equals ma, and then Ft is the only force in the x, which is why it equals ma. Again, we would sum all the forces together, but there's only one force in the x direction here, and it is definitely Ft. So Ft is going to cause acceleration because it's unbalanced. There's nothing else opposing Ft for box A. For box A.
How come the force of tension is the same if you don't have subscripts?
So remember, when there's only one rope, tension is the same. This is one rope. It's over a pulley. It may look like two ropes, but it's one rope that's weaved over a pulley. It's fed over a pulley.
Doesn't
I
matter
should say.
the direction.
Correct. Yeah. So let's write that down. That's a great thing that Valentina just noticed. She said, why is Ft not called Ft1 and Ft2? Because it looks like there's two ropes if you look at this correctly. It's one rope passed over a pulley. When a rope passes over a pulley, the tension on one side is going to be the same as the tension on the other. So Ft for this rope on either part is the same. Okay, the tension is the same for either. Yes.
So FT and like a problem with this would be the linking.
It'll most likely link these two together. Yes, it will most likely, in this case, it will link them together. Yep. Yep. The pail problem had Ft1 and Ft2 because they were physically separate ropes attached to separate objects. Okay, this is one rope that passes over a pulley. Now, that's my equation in the x direction. It does not give me enough information because we are trying to find tension and acceleration. And those are two of the three variables in the problem. So there's no way I can solve this equation. So I have to stop for mass A. Now, for mass A, what else could I write theoretically? So I'm going to put a line here. For mass A, what else could I write? Seb?
Ft divided by m equals acceleration.
We can do that, but besides that, Seb, sorry, an additional set of forces is what I'm asking. What additional set of forces for object A could we write? Vin?
Right in the y direction.
Yeah. Would it help us, though? No, it would not. I'm going to write it so you can see it. Okay, that's the sum of the forces. This is going to equal 0. Why am I crossing this one off and putting 0 and not this one? Valentina?
Because there's no motion change in the y direction.
Yeah, look, here's the object, right? Here's the box. It's going to slide to the right. It's not moving up or down. Again, it's going to, if it eventually falls, then sure, it will move up and down, right? But while it's on the surface, which is what we're going to be figuring out, it's not moving up or down. That's why AY is definitely 0. So the y direction only tells me that we've got Fn acting up and Fg acting down. So the y direction simply tells me that the Fn is equal to the weight of the object. That's great, and this is useful, but not for our problem. We don't need Fn in our problem at all. So this isn't really going to help us much. So although we wrote it here on the side, this is somewhat extraneous information. Okay, that's extraneous. It's not really used in this problem. But it is food for thought for future problems. So we have this statement still right here. And as Seb said, we could solve for AX or solve for FT either way. I agree. We're going to have to do that eventually. But let's now look at the second object because we haven't analyzed the second object at all. Here's where it's going to get tricky. Okay? I know, you're like, wait, it's been tricky. How is it going to get tricky now? Yeah. Okay, I know, right?
How much trickier is it gonna get?
Get ready for it. It's going to be a little tricky. Okay, so here's the scenario. Here's the scenario. Okay, two objects. Everybody see some? Same objects on the board. So watch what's going to happen. Ready? If this object starts to accelerate down, this one will accelerate.
That way.
Agreed, right? Is that logical so far? Okay.
Right.
To the right. To the right. Is that positive or negative acceleration?
Positive.
But down, what kind of acceleration is that?
Negative.
We see why it's going to get tricky now. So, listen, they're gonna move together. They're going to move together. If this has an acceleration of 1, this has an acceleration of? Very good. So it's not that tricky, actually. You all got it right away. That's something we did in AP. We did in AP, and there were a couple students even in AP that were like, wait, why did we switch the sign there? The idea is that the motion of the system is together. it's going to be either clockwise or counterclockwise. But for one of the objects, because we're considering down to be negative, this acceleration is going to be negative. So when I do this, I'm going to have Ft pulling up, the weight pulling down, and that equals m times negative a. That's where it's going to get tricky. A negative a. Now, what am I really calling that? It's really this. It's really a y. But I'm replacing it, right? That value will be the opposite of whatever we get in the x direction. So in the x direction, we should kind of drop the subscript at this point. Take a look at what I just did over here. Cross off your subscript now. Because ax and ay in this problem will be the same, just opposing numbers. So if this turns out to be 1, like we said, this will become negative 1, which is why the negative sign is here now. And again, use logic. If ft is positive and it's acting up, then fg is negative and it's acting down, well then down is negative. And this object is going to move down, so acceleration is going to be negative. But because I'm trying to solve a system of equations where a is unknown and ft is unknown, I need to somehow represent the fact that this is moving downward when this one moves to the right, to show that these signs are always going to be opposite of each other. If I don't make this negative here, it's not like you're going to get an answer and have to just switch the sign. It's going to be wrong. So again, if you forget to make this a negative, it's not like you're going to get an answer for a and be like, oh, I've got to switch the sign for it. It doesn't work, actually. Because when this is positive, this has to be negative. Or when this is negative, the other one has to be positive. The whole concept here is that when one object accelerates to the right, the other goes down. If this accelerated left, which way would this one go? Up. So if the x were negative, then the y would actually be positive over here. So the key is to recognize that the sign of A will be opposites. But the value of A will be the same. The magnitude, right? Magnitude, think about that word again. The magnitude of the acceleration is the same for both objects. Now, that's the key to this problem. After that, it's simple algebra. It really is. And for those that are like, oh, he keeps saying it's simple after this. If it's not simple for you, honestly, you need to practice more. Because from this point on, it's simple. The setup was definitely tough, and I agree with you, it's tough. But from this point on, this is simple math. This number is known, it's given. This is given, this is given. It's a system of equations. Ft and A are your unknowns. You've got to be able to solve this on your own. Okay, I'm going to plug in numbers that we know. We've got Ft minus the weight of object B is going to be mass times gravity. So 4 times 9.8 equals 4 times negative A. And then the first object is going to say this. Ft equals 20 times A. So once I've plugged in, it's algebra from this point on. You've got to be able to solve. I would personally here, I would move this over, and then you have Ft equals this whole thing, Ft equals this whole thing, set those equations equal, and solve for A. That's how I would go about solving this, because I think it's easier than using substitution method. You could substitute, obviously, a 20A right here as well. Right? Ft is 20A. That could go in right here for Ft. Put a 20A in, and then solve what's left over for A. But I like to set equations equal so I see it. Good.
Why'd you make 9.8 positive?
Because remember, where does the negative take into account, Julia? On the free body diagram. We talked about this about a week or two ago, that after projectile motion, G is always 9.8 now. It's not negative 9.8 anymore. Because remember the arrow is drawn down? And so you see a negative here because it was drawn down? So this negative already accounts for the negative that would be here. Okay? Because free body diagrams are different. They're not going to be the same approach as projectile motion. George?
If it's one chord, the tension is always going to be the same in that chord. Right?
Correct. The tension is the same or consistent throughout that chord. Absolutely. Maury, you got a hand up? You got it?
So now we can just set them equal to each other.
Yeah, I mean, just solve for Ft here. It's going to be negative 4A plus, what is this going to be? 39.2. And then these two equations are equal, 20A and this. So set them equal to each other. Do you see how your answer is going to change if you forget the negative sign? Look at where it carries down. Follow it. Look, right here, negative, negative, negative. So if you forgot the negative sign for acceleration, your answer will be wrong. It's not like it's going to be off by a negative sign. Again, if you forget the negative all the way up here, this would be negative, this would be negative. Well, if you forget a negative here, which would totally change your answer. When I move this 4a over, I'm going to add it to make this 24a, and then divide by 24. I would then be instead dividing by 16 had I forgotten the negative here. So it's absolutely going to change your answer. So when we draw our diagrams, we have to consider if two objects are moving together over a pulley, we have to consider if their accelerations are opposites or if they're the same. It matters a lot. Okay? What does A turn out to be in this problem? What do we get? What do we get? 1.63? And once we get A, we can plug that answer back in right here or back here, either spot. I would plug it in on the left one because it's easier, obviously. And we'll get tension in the core. It'll be the same tension either way. And you can check that by plugging this into either equation. Plug 1.63 into either one. It may be off by a small decimal because we rounded 1.63, right? So if we didn't round 1.63 and kept all the decimals and plug it exactly here and here, then our tension will pretty much be the exact same value. What are we going to get for tension? 32.7 approximately. You rounded and you rounded to 6? That's weird. I rounded to 7. All right.
Well, that was because I used just 1.6.
Got it. Okay. I might have kept the whole decimal the entire time. All right. So that's the tension that is in the cable itself. And that tension is the same throughout. The next problem, we're going to look at another pulley. So we're going to attack the same concept again here, but we're not going to look at something resting on a surface. So let's take a look. We've got what's called the simple Atwood machine. The Atwood machine is a classic problem of two masses hanging over a pulley. Let's make a first statement, and let's use logic. Just simple logic. Let's make believe for a moment that the surface isn't there. Okay, the surface is not here. If those masses were identical, what would happen? They would be at the same height. Very good. They would literally be balanced at the exact same height if they were identical. If the box is heavier than the metal cylinder, what happens? Use descriptive words.
Well, the box will go to the box, kind of like images, basically.
Yeah, like the image would be. The box would go down, and the...
The cylinder.
So what way would the system rotate? What way would it rotate? What do we call this direction? Counterclockwise, right? If the box were heavier. But if the metal cylinder is heavier, what's going to happen? All right? We see clockwise. So for these problems involving pulleys, it's really important to understand clockwise and counterclockwise also. That will help you. Okay, keep that in the back of your head. So let's talk about that idea. If the metal cylinder accelerates downward, which way does the box accelerate? So what's the thing with their acceleration again? Opposites again. So just like the last problem with the pulley, when one had a positive acceleration and the other was negative, we're going to see that appear again for this problem. Okay, so let's go ahead and take a look at this. So we've got the box here first. And then we've got the cylinder here. How come I've got an extra force on the box and not on the cylinder? What's that? What's the deal with that? Very good. The surface may be pushing back up with a normal force. While tension is pulling up on both of these objects, and then their weights are pulling down. And I'm going to call that object, what did I use, A or B in my notes? I used A and B, so I'm going to use A and B. Okay. Those are my free body diagrams. Why didn't I draw anything left to right here? Why not? What's the deal? Why didn't I do it?
There's nothing pulling in the left or right direction. It's just going straight up because only the rope and gravity are affecting it.
Only the rope and gravity. So it's got to be up and down here, right? There's nothing pulling left to right. There's no friction. There's no wind trying to push it. So left to right is empty. So how many how many equations can I come up with now, maximum? At a maximum, how many equations can I come up with? If I've only got the y direction for both objects, Juliet. Only 2. How about the last problem? How many did we come up with actually? We didn't use 1, but how many did we come up with actually? 3. We had horizontal motion, vertical motion, and then the other one was only vertical motion, right? Or forces, I should say. It might not be motion, really. So here, there's only 2 directions, 1 for each object. 1 for each object. So that means that I'm only at most going to have that many equations. So it looks like we're not given the mass of both. It looks like we're given the mass of the box, which is 15 kilos. But were we given the mass of the cylinder, actually? What are we given about the cylinder? What information? What is it?
The mass.
No.
300 newtons.
Absolutely not. Absolutely not. I just said we're not given the mass.
Weight.
The weight. I thought you were saying weight. Got it. You're given the weight of the object, not the mass. Again, this is given as weight because of the units. We need to know that here. So the weight of object B is 300 newtons. So can we compare these two right now? Are we allowed to compare apples and oranges? Honestly, can you compare apples and oranges in life? Yeah, I guess. If you were counting them, can you say 7 apples is more than 5 oranges? Sure, in quantity you can, but they're different things. Yeah, good. In energy, they'd be very different. Same here. We could say that 300 is definitely more than 15, right? But they're not going to make sense to compare them because 300 newtons versus 15 kilos are very different things. So what do you think we should do right away? What do you think, George?
Convert.
Convert what, George?
Newtons to kilograms.
We could do that. Yeah, I like that. Or?
Kilograms.
Good. So either way, so let's do that in both ways. So let's find the weight of this object and list it right here. And you know what? Let's find the mass of this object and list it up here. Because we're probably going to need both these things anyway. So how do I get the weight of this one? Well, 15 times 9.8. So the weight of that object is 147 newtons. Okay, well the other object, its mass will be what? I don't even have a number written down. It's going to be 300 divided by 9.8. What does the mass of object B become if we do 300 divided by 9.8? 30.6. So which object is heavier? Which object is more massive? Either answer, you can answer with the same answer, Mauro.
The cylinder.
The cylinder. The cylinder. So what's going to happen to this system? Since the cylinder is heavier, what must happen, Julia? It will move clockwise, good answer. It will move clockwise. The system will rotate in a clockwise manner. The cylinder will come down, the box will lift up. So because the box will lift up, what else can we say about this problem? If the box lifts off the surface, what can we say, George?
There's no normal.
There is no normal force in this problem, it turns out. It seems to be there in the beginning. But once we analyze the weight of each object, we see, oh, it's going to lift off. So the normal force does not play a role. God bless you. Does not play a role. Okay. As a result, our equations are quite simple now because normal force isn't even involved. So for the first mass, we've got the sum of the forces in the y direction equals the mass of object A times the acceleration of object A. For the second object, the sum of the forces in the y direction equals the mass of object B times the acceleration of object B. I'm using A and B as subscripts instead of y. Because if I put a y here, then it's AYA and then AYB. It just gets really messy. I know they're both accelerations vertically, so I'm not putting y. But what's the key to recognize for this problem again? If object A...
Their accelerations are opposite.
Yes, so on the next line, here's what I'm going to write. I'm going to write FT minus FGA equals MA times just A for now. I'm going to drop the subscript of A here. For the other equation, though, what do you think I'm going to write? For the other equation, what do you got, Maura?
It's going to be FT minus FGB equals MB times negative A.
Yeah. The negative A, again, plays a role here. Right there. So I'm replacing AA and AB with just A, and I'm calling one of them positive because this one's going to accelerate which way? Up. And which way will this one accelerate? Down. And because we're solving for A, we have to put the negative sign here again. If I had told you that the system's acceleration was 2 meters per second squared, this would be 2, this would be negative 2 when you plug it in. Again, if you're given the magnitude of acceleration, you got to know when it's up or down. Julia.
So with all the pulley problems, or most of them at least, there'll be like a negative A and a negative A.
Yeah. For a lot of these pulley problems, you're going to notice an A and a negative A, where they're going to play a role where they're going to be opposites each other. In section 4.8, we're going to get to inclined planes with a pulley over it. And that one's going to be a little trickier than this idea, but the same concept.
Basic pulley.
Yep, absolutely. At this point, it is plug and chug. Okay, so FGA we know is 147. The mass of object A is 15. FGB is 300. The mass of object B is 30.6. It's a system again. Now, in this system, just like the last system, tension and acceleration are our unknown values. Okay? Those are our unknown values. So we obviously answered the question, will it come off the surface? Yes. If not, what is the normal force? We don't have to worry about that because it did come off. If it does, what is the acceleration? So here's a question for you. You're taking a test and you're rushed for time and you have only 2 minutes left and you're on this problem, right? So what do? What do you do? What do you do? No, at this point, what do? You're trying to really get to the answer quickly. What do? A matrix works. I like the matrix idea. That works well. Graph it works. I like that idea. But more specifically, what do? You solve for what and what? The problem asks you to find the acceleration, right? Does it ask for tension anywhere? So what you should do is you should solve for tension and plug it in the other one to get rid of tension. You follow my logic here? If you solve for A, which is very tempting, because look how easy it is to solve for A. Divide by 15, you got A, don't you? And then you can take that whole expression and plug it in for A. But then that's going to end up giving you the answer for tension, which you don't want. You want acceleration only. No one cares about tension in this problem. So eliminate tension. The way to eliminate tension is to solve for tension in one equation and plug into the other. So I'm going to solve for tension right here by adding 147. Then I'll take this right here and plug it in for tension. You could also solve for tension in both equations like we did last time and just set them equal. That works also. For those that want to do that, you could solve for tension here, solve for tension over here, and set those equations or expressions equal to each other. But I'm going to just use the method of plugging in. So this becomes 15A plus 147 minus 300 equals 30.6 times negative A. I'm going to just make that look nicer, actually. Let's just make it negative 30.6A. Again, I'm taking this expression for Ft in object A and plugging it into object B's equation, yielding what's given on the bottom. Red is shown where it's substituted here. It's simple substitution method. Okay, now solve for A. A will become 3.35. So if you were answering for the system, your answer is 3.35 meters per second squared. But what about the cylinder? How would you give an answer for the cylinder? It specifically said, what is the acceleration of the cylinder, Juliet? Negative 3.35. The box, positive 3.35. But this problem says, what is the acceleration of the system? There's no way you can give both of those answers. So if it says the system, we're looking at this, and you could say what? Which way is it accelerating? What's the word? Clockwise. So a CW at the end of this might be useful. Clockwise. Because you're answering about the system's acceleration. Meaning both masses together are accelerating in a clockwise direction. Now, there is a general, I don't want to spend too much time because we're a little low on time, but there's a general solution to this problem. I'm going to jot it down so you can have it written. Okay? I'm still expecting you guys to show free body diagrams and work, but I want you to keep this equation in your back of your mind and for next year in AP Physics for multiple choice problems. Multiple choice, do you have to show any work? No. So the general solution is this. This is called the Atwood machine solution. It is the following. Larger mass times G minus smaller mass times G all over the sum of those masses. That will always give you the acceleration. Okay, you can try it yourself. I just can't spend time. We're running out of time. But here, look, this is where it would be solved, right here. See this equation? So forget everything here. Cover all this up. Forget any of this is here. Right here. If you solve this as a system for A, and you plug in mg or mbg and mag and solve this for A, that's what you'll get as a system right there. So if you were given a problem like this again, and it's on a multiple choice, probably won't be on the next test because that's tough for a multiple choice. For honors level, for AP level, definitely multiple choice. You can jump right to that solution and plug in the numbers you know, and you'll get this answer. And if you don't believe me, try it at this one. Okay, you could literally try this. You could say, okay, this is going to be the larger mass is going to be 30.6 times 9.8 minus the smaller mass, 15 times 9.8, all over the sum, 30.6 plus 15. Okay, if you do that, you will get, and I'm going to say approximately 3.35. And I say approximately because I think our answer was rounded initially anyway. Okay, meters per second squared. But that's a generic solution for the Atwood machine. There's a caveat to this. The caveat is this. We can't have anything else going on in the problem. If there's another mass, if there's suddenly friction involved, if there's air resistance, all those things change up this generic solution. So this is only a particular solution to this problem. A pulley with a mass on either side. Now, what if the masses were identical? If the masses were identical, what did we say would happen to the system? Acceleration would be 0. Well, try it. This number, if it's the same as this number, when you subtract it, what are you going to get? 0. The logic makes sense. If the masses were the same, it would be like 30.6, 9.8, minus 30.6, 9.8. Well, that would just give you 0. And that supplies or validates our logic from earlier that if the masses are the same, you're in a state of equilibrium there. Now, the general answer for tension is this. Tension is 2 little g, big M, little m, all over m plus m. God bless you. That's the generic solution for tension. And again, if the masses were the same, you would end up getting simply mg. The tension would simply equal mg, which is logical also. Because if this is pulling down with mg, and this is pulling down with mg, then the tension has to be mg on both sides. So if this turned out to be the masses were identical, and you call them both regular m, you'd get m squared here, you get a 2m here, m's would cancel, the 2's would cancel, you get mg. Okay, so these are the generic solutions for the Atwood problem. Okay? The generic solution for the Atwood problem. Okay, there's tension and there's acceleration. Those are the two. All right, we want to do 2 more today. We really want to get through these last 2 problems. Example 11 looks tricky, but once I show you the method for example 11, you're going to be like, dang, this is actually not that hard. It really isn't. But the first time I did this problem in high school, I thought it was tricky also. And here's the thing. There's a small little tidbit you kind of have to know. And here's the tidbit. It looks like there's only one mass here. Would everybody agree with that? Yes. Right? There's only one mass. So if I drew a free body diagram for mass 1, let's draw it together. Here's mass 1. I've got the weight of object 1, and I've got the tension in the third cable. That's my free body diagram for object 1. And if you look at this problem, you're going to say, oh, this isn't going to do much for me. How can I find the tension in the other chords, right? Because what will this give me? This will give me FT3. I know what FT3 will be because this object is not moving. It says determine the tension in each chord for the arrangement. So if this is the arrangement, nothing is moving because it's all chords. So as a result, tension is going to be balanced by this. There's no net force, so these are going to be adding up to 0, so these are going to be balanced. So I can get tension 3 right away. Right, I can do that. So let's go ahead and say, for this object, the sum of the forces equals ma. That's going to be 0 because it's not moving at all. We've got tension pulling up. We've got the weight of this object pulling down. So the tension pulling up will equal the weight of the object pulling down. So the tension is going to equal the weight or the mass times gravity. So there's my solution for the tension in the third chord. That's the easy part of this problem. And at this point, this is where most students get stuck because they haven't seen this problem before. And what I hadn't seen before, I was also stuck. Because I can't go any further. There's no more masses to write a free body diagram for. None. Any ideas? Any suggestions as to what we may be able to do? Carolyn, what do you think?
Two other ropes kind of part of the tension that's holding up the ball.
The two other ropes, are they part of the tension? They are. They definitely are. Those two tensions pulling kind of combat the other tension pulling, right? So they're going to play a role. So you're on the right track, but I need more of a guideline as to where to go next.
Maybe use the point where the three ropes meet, and then the mass is zero, but he's like somehow how gravity's affecting it.
You hear that? You like what she's saying? See the dot there? It's not there for just like a reason. It's like, oh, why is there a dot there in the middle of the ropes, right? That dot is because the book wants to give you an idea where you're supposed to go. So here's what you do. And this is a very useful technique. Write it down if you need to. You can draw free body diagrams of knots. K-N-O-T, knot. When you tie a knot with several ropes pulling from one location, you can do a free body diagram of that location. And as Christina just mentioned, the mass of a knot is considered to be zero. So we could say, and not only that, the acceleration is also zero, so the mass doesn't matter at all. But we can do this. Our free body diagram at the knot would look like this. Tension pulling down on the knot, tension pulling up on the knot, up and right, and then tension pulling up and left on the knot. So there's my free body diagram of the knot itself. Now, there's no mass of the knot, so there's no weight vector pulling down here. There's physically no weight acting on the knot. The tension in this rope is connected to the knot, so tension pulls down. The tension in these ropes are also connected to the knot, so those tensions pull away from the knot. Remember, tension can only pull. So at this point, it's simply a state of equilibrium again. Now, the hard part about this problem is that we've got a couple different forces, right? We know FT3. We got it. It's right here. Mass is 8. 8 times 9.8. We've got FT3. So that's done. This is nice. This is easy. We need FT1 and FT2 now. So let's think about how this works. Here's where your geometry plays a role. I know, right? You always say, right? Where's that geometry going to play a role? Here we go. So, look where I drew that dotted line, please. Look at the dotted line here. The angle theta 2 is also this angle theta 2. The angle theta 1 is also that angle because they are alternate interior angles. And you got to know these phrases. I mean, or at least know what they mean on here, right? You got to know, actually, you need to know the phrases at all. You need to know that these are the same and these are the same. That helps me with my free body diagram now. Okay, so on the free body diagram, let us label. We know that this angle here is called theta 1, and this angle here is called theta 2. Again, it's not given that way in the diagram, but I'm writing it that way in my free body diagram because I always want the angle between the force and the horizontal. I want the angle between the force and the horizontal. Here's the force, here's the horizontal. I do not want this angle here at all. Again, I don't want that angle between. I know the bell, right? Give me another minute, it's your last period. So as a result, here's what we write. In the x direction, I'm going to move stuff over so we have a little more room. In the x direction, we've got sum of the forces equals ma, since the mass of the knot is 0, and because the knot is not moving, A is also 0. So either way, that is definitely 0. We've also got the sum of the forces in the y direction. And that is also going to be 0. The knot is not moving and has no mass. In the x direction, I've got FT2 pulling to the right. So what's the x component of FT2? What is the x component? Remember, components of vectors. How do I find the x component always, Isabella?
Take cosine. It's like
Yeah.
FT2 cos whatever the value is.
Very good, which is we're calling theta 2 for now. I agree. What's pulling to the... I'm going to write it in. Yeah, I'm going to write the numbers in a moment. I just want to write the actual values first, or the variables first. What's pulling left is ft1, but only its x component. So we put cosine theta 1 there, and that equals 0. That's the x direction right there. Now, this is very much like the Tom Cruise example. Think back to the Tom Cruise example on the tightrope. Except here's the difference. Or what is the difference? The angles are not the same, right? So ft1 and ft2 are not going to be the same value, it turns out. Okay, they're not going to be. Now, finally, in the y direction, we've got watch this one, ft2, y component, is pulling up. ft1, its y component, is pulling up. And what's pulling down? What's pulling down? Yeah, how much of ft3? All of it. All of ft3 is pulling down. Because ft3 is acting downward, so there's no sign of theta. But because ft2 and ft1 are both at angles, we know they're both pulling up, so they both get positive signs, but only a fraction of them is pulling up. Now, you know the numbers for thetas. Given. This value can be calculated from right here. So you know this, you know this, you know this, you know this, you know this. So what's unknown? What's left that's unknown in this problem? What's the only variables left unknown once we plug in all our thetas? ft1 here, ft2 here, ft1, ft2. So it's two variables, two equations. It's again a system of equations. Yes. Okay. So here's what I'm going to do. Before you guys go, I want to show you the plan for attack for the next week or two. I have it with me. I purposely did this ahead of time, so give me a second. Here's our plan of attack for the next week or two. All right, here's our plan of attack. Ready? So today we're finishing. This is your row right here, guys. Today we're finishing 4.6 and 4.7, which we spent a lot of time on now. We're going to have Christmas break. We're going to come back. I'm going to give you a quiz on 4.6, 4.7 when you get back. The first day. I'm telling you that. I know. Then, listen. Then you're going to have the beginning of 4.8, which we're going to start talking about friction, the introduction to friction, which we've already talked about in our lab for Lab 8. We've kind of alluded to. Then, listen. Then we're going to have Lab 9. It's going to be a physical lab, not the simulation. We're going to do Lab 9 this day. Your lab binder is due this day. It will not include Lab 9 because we're not going to have finished it. If you're not sure what should be in your lab binder, which I told you on day 1 of this course, you should try to check Moodle because I put all the information there underneath what the due is for. On the homework section, I put all the information on what should be in your lab binder. Your binder can be a binder or a folder, is fine, either way, but not electronic. I want it to be printed. So that will be due on the same day here. Your test was originally, I think, this day or this day. I moved it all the way to this day so that we could have another day of 4.8. Your quarter project is due on this day, so get your quarter project in. We'll then have a test here. We'll then test the quarter projects on this day. So your quarter project is due on Friday the 10th. We will not test it until Thursday. If you are late, you will lose 10% every day on a project. So you do not want to be late for this project and think, oh, we're not testing until then, it doesn't matter. It does. Get it in when it's due. You've known about this deadline all quarter. Throughout this week, you'll notice there are homeworks due. So Lab 8, which you already pretty much finished, is going to be due this day because I want to just touch on friction before you turn it in. Then you're going to have something else due this day. You're going to have something due this day. There's a lot of stuff due each day after break. So what you really need to do is make sure that you look at Moodle and that you outline exactly what is due when. Okay, this is a nice outline of after break. Okay, from this point on, you'll have Lab 8 due, you'll have your binder due, I tell you what to submit, what not to submit. You'll then have your project due, you'll have homework for 4.8 due. This, I made an extra problem set if you want to. I won't count this against you, but I would recommend doing it. This is just an additional set of problems I put under documents and handouts. It's called Chapter 4 Forces Problems. I thought I'd make more for you. Then problem set 4 is due on the day of your actual test, and then that lab is going to be due after the test. So please mark this off in your agenda. What should you definitely get done over Christmas break? Project. What should you probably start? If not, you'll always put done over grade. Problem set. Is that clear? Okay, 4-8 homework and problem set is not online yet. So if you're really trying to get ahead, you really can't start 4-8 yet, but we haven't even touched it yet. So I would do everything up to 4-7 if you were really trying to be a go-getter. Okay? Alright. Go get at it. Office hours, you want to hang out? At office hours, now you want to hang out. I just spoke. I know. That's not doing for the test. I'll probably still be here around. It's not over here. I know you're coming back already.
I timed it. Like, I understand I got these.
Kids have a concert anyway.
Because then we can control the time, set, the angle that starts with, we can control.
I already submitted the video, but I just did, I don't know what math to do, so I just used the normal force and I plugged in to find the acceleration and explained it.
Perfect. That looks good. And the normal force is the scale that you read.
Yeah.
Right?
Mm-hmm.
I love
And then
it.
I converted it into newtons.
So you submitted a video of it,
Yeah.
and then you're also submitting this, right?
You
put that in the video?
I put it in the video like 5 times.
Awesome. That's perfect. That's what I'd rather you do.
Yeah, if you want to see, then you have to pause it because I want like for like 2 seconds.
But all the math is contained in the video.
Yeah.
Nice work. That sounds great. Thank you, Valentina. So for example 12 here, we're looking at a small mass that's hanging from a thin string and can swing like a pendulum back and forth. You attach it to the window of your car. When the car is at rest, the string hangs vertically. What angle does the string make when the car accelerates at 2.5 meters per second squared? And then what is the angle when the car moves at a constant velocity? So if we think about it, if the car were moving forward, and we think about this on like a train, the mass would suddenly act backward or move backward like this. So that's the direction it would move. So really, eventually we're going to be finding this angle theta to see how far it moves back. But for the sake of this problem, when we draw a free body diagram, we can draw it slightly differently. So let's draw the object itself after it gets pulled back a little bit. We know that the weight acts down, so we've got Fg here, and we know that tension acts in this direction. And for now, I'm going to call this angle, for the sake of this, I'll call it beta. We'll use theta as the other angle there. So if I'm looking for beta in this problem, that's what I'm trying to figure out, I have to ask myself, okay, what are the sum of the forces again? Well, in the x direction and the y direction, we have separate parts. In the x direction, we could say the sum of the forces equals max, and in the y, the sum of the forces equals may. Now, it's not accelerating up or down, so this drops off. It is accelerating left to right because the car's acceleration is given as 2.5 meters per second squared. So if we're looking in the x direction, we're looking here at ft cosine beta, and that's going to equal max. And then if we look at the y direction, we're going to have ft sine beta minus fg equals 0. So again, what am I doing? I'm taking this component of force and thinking, well, there's ftx right here, which is really ft cosine beta, and there's fty here, which is ft sine beta. And remember, once we plug in those values and we write it that way, we can kind of just cross this off of our free body diagram, and it's no longer there. So the diagram we're seeing now is where I came up with these two equations. This is the only x force, and that equals ma. There's got to be acceleration if there's an unbalanced x force. But in the y direction, we've got the tension pulling up right here, and then we've got gravity pulling down, and those are balancing each other. And again, the idea is that once this object starts accelerating, the mass itself will be at a constant angle theta that won't change. If theta were fluctuating, then ay would be a value that's not 0, and we wouldn't be able to utilize this part of the problem. So if we take a look at this, we're going to see that what we want to really find here is we want to determine the value of angle beta. But unfortunately, we can't get beta unless we know the force of tension in the problem. So we're going to have two unknowns here and two equations, which again gives us a system. So we've got ft sine beta over here minus mg equals 0. And here we've just got ft cosine beta. And I'll put here, I guess we could say, equals just max still. M and ax, let's see, is m given? M is not given, which tells me that it's probably going to cancel out at some point in the problem, since we're not given a value for it. So let's go ahead and solve for something. Let's solve for ft over here. So I'm going to move mg over by adding it. I'm going to divide by sine beta to get ft by itself. So I'm going to take this expression and plug it in right here for ft. And that'll give us mg over sine beta times cosine beta equals max. So m is indeed on both sides. That'll cancel. So on the next line, let's see what we get for this. We're trying to find the angle itself. So we've got g cos beta over sine beta equals ax. Let's see. If I want to get theta or beta by itself here, I can move g over by dividing. I get cosine beta over sine beta equals ax over g. Cosine over sine is really cotangent, but that might not be familiar to you, so maybe we're going to invert both sides. And if we invert both sides, we get sine beta over cosine beta equals g over a. And this is more familiar probably. This is the tangent function. So this equation then becomes tangent of beta equals g over ax. So beta equals the tangent inverse of g over ax. So that'll give us the angle beta that we're finding here. But really, once we get an answer for beta, beta will turn out to be, looks like 75.7 degrees. Well, that angle that we get as an answer is really the angle with the horizontal. Let's point it out where we're talking about here. The angle beta, if you remember, was this angle right here. I'm drawing it in blue right now. That was beta right there from earlier. But we want this angle theta up here. And this angle theta is the complement of this angle beta. I can figure it out by just drawing a triangle. If I zoom in on this region, I can think about finishing off my triangle here. Well, this angle right here, that was theta. So the angle theta is in the upper corner. Beta is this angle right here in the lower corner right there. That's beta. So we know if we get 75.7, then the angle that we're looking at, theta, would turn out to be equal to, in this case, what is that, 14.3 degrees. The last part says, what angle does it make if the car is moving at a constant velocity? Well, that problem becomes tricky at first, but it's really not that bad. If it's a constant velocity, we go back to this part right here, and it says that beta would equal tangent inverse of g over 0. And why am I putting a 0 there? Because that's acceleration, and a constant velocity means acceleration is 0. Well, the only way for this to be true, right? The only way for this to be true, let's go back and resolve this. Let's go back to saying this is tangent beta equals g over 0, right, by moving the tangent inverse back over. The only way for this to be true is to recognize that tangent, again, is really sine over cosine. So really, the only way for this fraction to be true would be if cosine beta were equal to 0. Because this is always going to be 9.8. So if cosine beta were equal to 0, that would mean that beta, in this case, would be equal to 90 degrees. And if beta is equal to 90 degrees, then theta would be equal to 0 degrees. And a theta of 0 degrees simply means that the object is hanging straight down. And this object is in a state of equilibrium if there's no acceleration acting on it.